Good?
I think we have to do it here.
Oh, you do it here.
Yeah.
Thank you.
As of course, make sure everybody is on the cloud.
Sorry, you want to mute the computer because the meeting is.
Now, good?
You want to mute the computer and then the source.
This one is mute.
No, but the mic, you're not the mic.
Yeah, I did. Oh. Now good?
Yeah.
Now I cannot. Oh. So I just want to introduce the group that works on large-scale catalog computations at Lamont. It's Kai-Wen Wang as a postdoc at Lamont, working on supervised machine learning for catalog earthquake catalog production, mainly using Quakeflow with Wei-Jiang Zhu. Then Eric Posey, who's working on template matching. He's not here, he's in France. And machine learning as well, and beamforming. And Teresa Sabi, who is here, is now a postdoc at Lamont. Postdoc at the USGS, used to be a student at Lamont. She's working on unsupervised machine learning for spectral feature extraction. And she's going to talk this afternoon. There's a change in schedule. And then David Schaff, who has been at Lamont for quite some time. He is a master of all things waveform cross-correlation for detection and delay time measurements. And myself, I'm a co-PI on this proposal, and I've been working on precision seismology and analysis of large-scale earthquake catalogs for, I guess, too many years. I want to acknowledge Nate Grosvenor, who's helped us tremendously with putting things up in the cloud. He does a lot of help. He did a lot of help with unsupervised machine learning tools, SpecUfx, refactoring it, and then Wei-Jiang Zhu, who is working with Kai-Wen on making Quakeflow part of our workflow. So we already went through this. So this is, I'm giving a couple of examples of what we did over the last several years and areas that we're working on right now in terms of producing such high resolution earthquake catalogs. So on the left, you have California. That's our old playground where we developed a lot of those tools. By the way, those are all density plots. So they show the density of earthquakes within bins. That shows you more like where the active faults actually are, much more useful than dots that superimposed. So you can see the scale from left is 200, hundreds of kilometers to tens of kilometers in the middle in central Italy. The 2016-17 Amatrice sequence, And then on the right is axial seamount. That's a few kilometer dimension. And you can also see the number of stations. On the left side, it's 1,000 stations. In Italy, it's 130 stations plus. And then at axial seamount, we have 7 stations that are OBS, of course, on the water, cabled to the shore and sending data in real time. The number of earthquakes on the left is in California, we now have 1 million earthquakes over 40 years. In central Italy, we had 1 million over 1 year. And at axial seamount, we now have about 150,000 over the past several weeks, but several years. But the most of those earthquakes happened during the eruption in 2016. No, 2015. So you can see the title here, large scale, refers to the spatial scales. The high density is when you have an area where you have lots of earthquakes. High rate is when you have an area where a time period where you have a lot of activity, like in a volcanic eruption or an aftershock sequence. High resolution. So for us, high resolution is in the tens of meters. For others, it's hundreds of meters, but we strive to get down to the scale of individual earthquakes. So at the magnitude 2, 1 level. So we can actually learn something about the source or the interaction between earthquakes. And so deep magnitude, I use that to describe that we are trying to lower the magnitude threshold. So going from network minimum magnitudes by an order of magnitude down. So with every order of magnitude lower, of course, you increase the number of earthquakes, which stresses the computational load again. So we're trying to all of those examples were computed on a server that was kind of optimized for those kind of problems. So fast I/O, and then for the inversion, lots of CPUs. So it's not HPC, but it's also not the cloud per se. So we do need a fast access to the data to relocate those events. And you can see that those examples are at various stages of processing. On the left, we use cross-correlation, double inference, and run everything in real time. In the middle, we have central Italy. I'm going to get to that in a few seconds. Explain more what we do there. And then axial seamount, it's probably the most complete workflow right now that we have. Supervised machine learning for phase picking. Then we have unsupervised machine learning for event discrimination, discriminating between different earthquakes and ocean noises, like whale calls. And then we have cross-correlation to get the differential times. And then we have double difference to relocate the whole thing. And we run everything in real time. So if you want to access those real-time websites, the one for California is NoCalDB, and the other one is Axial DD at ldocolumbia.edu. I would do that right now, but it's going to screw up the whole thing. So I showed this on Monday. So it's essentially a message that I want to say again, that when you develop a catalog, you want to have a purpose. You want to have a research question you want to address, because you can get a very detailed, very high resolution earthquake catalog for example, to look at repeating events we do in California, where we're getting down to tens of meter resolution in terms of the spatial precision. And once you have that, the temporal periodicity falls in place too, because you separate the random events from the repeating earthquake sources. And you can use that for various applications like measuring slip rates and so on. Then if you want to have a high resolution earthquake catalog, you want to include cross-correlation data and do the whole thing so that you can actually image the faults. I'm getting to that in next slide. And at axial seamount, we used unsupervised machine learning to detect some of those precursory signals, which we call mixed frequency earthquakes that are related to movement of magma volatiles ahead of the eruption. So they start about 15 hours before we can track the eruption at the sea surface at the ocean floor. So those are all examples of what we can do with CAD logs once we relocated them. And when we put them into a real-time system, then we can actually, they're useful in tracking eruption preparation, for example, or prepare for eruptions. So just a few words on the central Italy. Since we have a special guest from INGV, Claudio. Oh, he is working. It's okay. So that's the 1617 earthquake sequence that started with the Amatrice event. And you can see the evolution of those catalogs going from top left, the routine location produced by the INGV network. And then it continuously progressed to, at the bottom right, the application of PhaseNet to the continuous data, which yielded about a million or over a million earthquakes. So on the way there, we have bottom center, we have one where there were repicked earthquakes and then cross-collated and relocated. And so the one in the center middle is the highest resolution, but not the most complete. The one on the right is the most complete, but not the highest resolution. So if you want to do statistical analysis like p-values, you pick the lower right. If you want to do detailed structural analysis, then you can pick the middle one, and so on. So the top has, I think, about 60,000, top left about 60,000 earthquakes. The middle panel has about 500,000, and then machine learning base has about 1 million earthquakes. And you can see on the right the fall off of the minimum magnitude in those catalogs. So just an example from the cross-collation based catalog, which has the highest resolution. So there's you can image the fault zone, the fault geometry of those faults. So you can see the normal faults, some conjugate faults, and then in blue you have the detachment. And if we zoom into a cross section in the middle, you see the normal faults that is truncated by the horizon. It has some sort of what we interpret to be a bookshelf structures that's activated during the North Sea earthquake. So those are the kind of things we need to keep in mind when we develop those catalogs. It's like, what do we want to resolve? How good does our resolution has to be? Again, those are density plots that show where most, it's either density or moment maximum or moment plots. I think it's density plots that show you where most of the activity occurs on those faults. Now, one other aspect in this whole research is that the single event location it's pretty straightforward. You have an earthquake, we have hundreds of stations, you have PICs, PNS, and whatever, but the data and the amount of data is limited, and every earthquake is located one at a time, so it doesn't relate to any other earthquakes nearby. So when you do relative location, it's different because you're measuring delay times across large areas. So on the left side, you see a density plot of the number of the percentage of correlated events in California. And you can see, obviously, along the San Andreas fault, you have almost 100% of events that correlate because the San Andreas fault in south of the Bay Area is very smooth. So it repeatedly ruptures in earthquakes that are very similar, producing similar seismograms. And so you can get very high correlation waveforms. Highly correlated waveforms. So there's about 1 million earthquakes over the 40 years in that catalog. And so we have continuously computed correlation delay times from this data. And you can see on the right, the increase in the number of measurements. So we're now at 10 billion correlation measurements for Northern California. And so those 10 billion correlation measurements is useful. They're useful data for relocation. So they're all above 0.7. So that means like the number of correlations we actually do is much, much higher. But the other problem that comes up is obviously there's no way you can invert 10 billion delay time measurements. So we have to be very smart at selecting the best and finding a system where you can access that data efficiently. And so the idea is to retool those tools that we optimize for servers to work in the cloud. So the idea of SCOPED is to at least, start moving some of those tools into the cloud, so it will be easier to run to produce such catalogs. And that's especially important now, timely now, because FaceNet is able to produce very consistent picks. So before we relied on network picks, which if you don't know the network or the analysis picking the data, it will be very difficult to assess the quality of the data. So with FaceNet, if it's trained well, we have a very good base of using that on a large scale. So again, the idea is we have continuous data and data products. We use that to estimate parameters, magnitude, locations, whatever. And then we can use that in precision seismology to get high resolution earthquake catalogs, and then we can do analysis or new ways of analyzing that data. And on the right side, you have the discovery part, where you can use those catalogs to explore, for example, spectral variation in a source or the media. And that's what Teresa is going to talk about this afternoon. The way this looks in a more flowcharty way is you're all familiar with. So what we're trying to do is assemble modules that we can plug in and leave out whatever we want, whatever catalog we want to produce. So you go from the basic flow is we go from detection to phase picking to association to location to correlation to relocation and then to visualization. And then we plug in a source discrimination part, or we can plug in a template matching part, and then we can relate that to a spectral analysis to research or discovery, and then which it also includes clustering in terms of separating events with similar characteristics. And we do this all retroactively or in real time. So today, we're gonna do the top part on a very small data set, 1 day of earthquakes in Amatrice, about 1,000 events, and then use that to demonstrate the workflow in the cloud. And then this afternoon, Teresa will talk on this on the unsupervised machine learning part. We have not implemented source discrimination at this point. We have not implemented template matching, but those are all tools that hopefully we can plug in, containerize, plug in, and run on a data set. Now, I have to make a comment here that that workflow that we have prepared is tailored to that 1 day of Amatrice earthquake. So it runs FaceNet, which produces a certain amount of accuracy in the picks, which we then treat in the follow-up processing. So if you plug in a different earthquake at a different waveform data stream from some other region, you have to work on tuning those parameters. So why do we do scoped? So the olden days looked like this. So I want to acknowledge, a lot of people worked very hard on producing software coding the old way, and sometimes very frustrating. Sometimes it works, sometimes it's not. Some people made it, some not. But scoped, the idea of scoped is to move this to a new generation, which I call as a scope phase. So I should mention that while he is resting, he's deeply thinking about the problems. But he doesn't have to think about how to run the code. So I want to end with that. And I think we can move now to Taiwan with introduction to FaceNet and getting on the cloud. Can you just plug that in here?
Plug in, and I need to screen share, I think.
Yeah. Oh.
Here? No, still sharing the right screen?
Yeah.
Okay, okay. Hey, good. So, so I'll next give you some brief introduction on the ML models we use for this tutorial, and also at the end I'll just tell you how to run this model on the cloud, and probably troubleshooting whatever issues we might get. So this is so we build a container with different modules of using machine learning method, and we basically here we are trying to build a framework that contains each of the component from the very beginning, the inputting continuous raw data to at the end we'll get a double difference relocated earthquake catalog, and later on you can use this catalog for other processes. You can either look at the structures, or you can also do, say, unsupervised learning that Teresa will introduce in the afternoon. So like we in this workflow or in this tutorial, we select certain models to do peaking association or like correlation, but you can use also other models, either if you retrain FaceNet or if you want to use EQ transformer or some other machine learning models, you can replace those modules, but you just need to add them into a container by editing the Docker file and then building the container. And so I like to start with the machine learnings in seismology. So especially during the last decade or so, there has been a lot of applications of all these different machine learning models, either supervised or unsupervised machine learning in seismology. And on the left, I'm showing you the comparison of catalogs from like the routine processing, and on the right here, this one is the one coming out of the FaceNet pigs and the machine learning workflow. So you see that there's orders of magnitude of increase of the earthquake catalog size. And for the catalog here, this come from the 2016 to 17 Central Italy sequence. And this is also the same region that we are going to run the tutorial today, but we only choose one day from the entire year of the sequence. And this machine learning catalog includes around million of earthquakes in that 1 year. And in our tutorial today, it's like a simple, very simple demo case. We only choose one day, so we have roughly 1,000 earthquake in that day. But they just give you a taste of how you can run the whole entire workflow from the beginning to build a relocated earthquake catalog. And to scale it up, you can just since we are running it on the cloud, you can just choose create a larger instance that give you more CPU power, and then you can also expand the time range from 1 day to say longer time. But just be careful that you probably need to fine tune some parameters when you either choose another time range or if you apply to another region of the data set. And on the right, I'm showing all the different tasks that can be done by machine learning models. There's a lot of works that focus on data processing and automation of the current, the routine processing modules like phase peaking or detection or polarity peaking or whatever things that you do regularly. And there are also other related tasks like inversion problems or forward modeling processes. And also there's some, but not that many applications using machine learning on data mining or exploratory data analysis. And we see that though those data, or those tasks, they all need different size of the data sets input as training or either as exploration, and they run on different type of inputs, either synthetic data or they can be real data, continuous data, or waveform data that you can get. And for example, here, this darker color circle, that's for phase peaking. That's very popular topic in machine learning, and it is very data extensive. It uses a lot of data from our previously historical catalog that are generated by those analyst picks. And we're just in this task, we just use machine learning models and try to learn how the analyst would pick a waveform for arrivals or for other properties you're interested in. And when we train the model, we try to reproduce, or we try to reach the level of accuracy of human analysts, and we also try to make it more robust, or make it having a more uniform performance on different data sets or over time. And just let you know that there are a lot of models available using machine learning. There's a lot of pre-trained models, or there are a lot of models that you may retrain yourself. So if you want to plug in new models, you can just refer to the scoped template. And I think Ian has give you some introduction of entry-level containerization on Monday of how to use those scope template and how to edit those Docker files to containerize a new model or your own version of the model that you want to use. And you can also find some examples from the scoped projects on this website. So here in this tutorial, we are using a workflow that is shown here. So we start from the continuous waveform, and we first apply FaceNet to pick the phase arrivals, and then we use gamma, which is an associator, to associate the peaks into events, and then we locate them using a very classic location algorithm, hypo inverse, to get the initial locations, and then based on those locations and peaks, we do cross correlation on the event pairs to measure the correlation based delay times. And we also and lastly, we use the cross correlation measurement and also the peaks in the double difference relocation to get like a final relocated catalog. So I just want to note here that in this tutorial, we are downloading data into the container, but if you, or there are probably already some data sets available on the cloud itself, on the AWS. So you may be, you could have like even faster access to the data without having to download it to locally. And just mention that I've tested on the same workflow. If I download the data locally to my say my laptop, it takes much longer than if I run it on AWS and download the data from data center to the EC2 server. So that there's a advantage in data downloading as well as also the processing. But like probably in the future, if you already have data there, you probably don't need to download the data from the data center. And just to give you some brief introduction, I think many of you already used or heard of the machine learning models like the FaceNet, which is very famous one, and is widely used on all different data sets. So this is the deep learning model. It's a convolutional neural network that is trained on the millions of analyst pigs from Northern California. And this is a kind of a UNet structure that gives you like a feature mapping or probability mapping of the P wave and S wave arrival on top of the original continuous data input. And I'm showing an example here of the phase peaks. So this is on the top, I'm showing the 3 component waveforms, and the bottom channel showing the P and S predicted probabilities for those arrivals. So it has arrival peaks on the maximum probability, and also it has a distribution that can basically tell you how confident the network is on this peak. And you can use this information as a score in, like, for example, location or something. And in this container, we are including a new version of FaceNet called FaceNet Plus. So it is a multitasking model. So it does train the model to pick the phase probabilities, like shown here, the P wave and S wave peaks. And also it has also other outputs like the polarity peaks. And also there's an output of event probability that gives you some like it gives you some actual information on whenever the model thinks there's an event. So this model is available on GitHub, and we are using this new model here to detect phase peaks. We do generate polarity information, but we don't use it in this tutorial notebook for now. but I just want to let you know that those informations are available. So if you want to calculate, say, focal magnetism or using hash or some other program, you just need to add that module into the container, and then you can use this probability, like polarity information in calculating like moment focal magnetisms. And so next, for association, we use a model called gamma, which is a Gaussian mixture model associator. So this model this model uses the phase peaks move out and also the amplitude information to try to fix like most likely move out with the decay in magnitude, decay in amplitude to associate peaks into events. And so there are also other possible association model that you can use, but this one is kind of simple and straightforward to use. But there are some hyperparameters that you may need to tune if you have like based on the catalog you generate or the peak qualities. So we have this tutorial of how to run this this workflow on the cloud, and I put it on GitHub, and I probably should paste it on Slack channel or like so that they can just anyways, I'll paste it later on this on Slack channel so that you can go through this notebook and just follow the steps there to launch an instance and run it on the cloud. And yeah, and we currently run this demo notebook on the cloud, and probably the next step will be doing real-time production. So that's here I'm showing an example that we do at XOC mount. So we're running the system in real time but not on the cloud yet, but we'll be working on it. So this catalog this is a catalog we do for seismic monitoring at XOC mount, and it uses 7-station OBS data and it streams data in real time, and then we does real-time processing of phase peaking association and event location and also relocation. And finally, we do event classification to track all different type of sources, including earthquake sources and also oceanic sources or volcanic sources. So we have this real-time website running here. And if you want to take a look, we can just scan the QR code. You can just use the link. So we are showing the real-time activities in the map there, and the red dots are showing the most recent activities from yesterday, from the past 24 hours. And we also have the links to the individual waveform. So if you click on each of the link, you can see how those events, for example, something like that, you can see the events on each of the stations and their linked events in the relocation processes in the base catalog. And I think I'll just next I'll be showing you some hands-on work, like we will be logging into AWS the same way as you did on Monday. I hope you still remember it. And we will launch a new instance, and then we will pull the container the Docker image to your new instance and running it. So I just okay. So oh yeah, just to mention that I think everyone will have a like access to the AWS cloud and including the remote attendees. And there will be more sessions using the AWS cloud in this afternoon and also tomorrow. So we are basically following the same process, launching the instance and running, pulling the Docker and running the Docker in there. So I hope you'll be familiar with it later. And there are also options to run it locally, but like here just for easier debugging or something, like we will ask you to run it on AWS cloud. You can use this link to log in and wait, so I just so the default password is scope 2024 at UW, but you probably already have reset it on Monday. Yeah, you should use your new password. And I also no. So everyone log in already? Okay, good. Okay, I will log in. Okay. Okay, I already log in. Okay, good. So just so if you log in, no, I can just log in from the beginning and just show you how to do it. So I'm logging in here. And this is what you'll see after you log in. And you go to EC2. And you click the launch instance. And you can name your instance whatever name you can find, just saying -ml. And then here you choose the Amazon Linux AWS. Not there yet. Not there yet. Everyone with me? And next, you choose the architecture to be ARM instead of the AMD X. You want to make sure it's ARM, otherwise the on Zoom. Oh, I'm sharing Zoom. I think I'm already screen sharing. No,
That's good.
now I'm sharing. Okay, sorry. So everyone with me, you need to choose architecture as ARM. And then for the instance type, you can do you can actually try whatever you want, but like I'm just saying that if you choose this one T4G 2x large, it will take roughly 25-30 minutes to run the entire notebook. And if you choose, say, this one C6G 8x large, it will take roughly like 15. Oh, like, okay, okay. So if you choose a larger one, like this one, where am I? Like this one, C6G 8 times X large, it will take you roughly 15 minutes to run the entire workflow. But so you can try whatever you want, but just to note that there's the cost is showing here. So you see that this one is larger, it has 32 CPUs, but it's also more expensive. This one, the T4G, this one is much cheaper, but it's like only 8 CPUs, and it will take longer to run the same workflow, the same amount of data. So depend on your depend on your preference, or like if you can wait or not, like you can choose either the smaller one or the larger one. But
It's possible. Did you understand what we just talked about? Can you hear from the back? No. That's why, okay, I want to make sure we portray voice.
okay,
Maybe we get the mic. You can choose instances if they are cheap and small, it will take longer to run. They need to have at least the memory required to load the container and the data. So that's the minimum, right? They have to be big enough in memory to have your container and the data you want to load. A cheaper one, the T2s and T3s and all that, they're small, they're cheaper. It will take longer because it's not parallelized as much, or you won't parallelize over as many cores. Or you can go for bigger instances, the C's. They are a lot more expensive after 3 or 4, but they will be faster to run. That makes sense? Okay, so we can start that. I wanted to introduce also the on-demand versus spot instances. On-demand is you get the priority for the instance to launch. Spot, you will have a lower priority and a lower cost. So unless you're doing early warning, I think spot is fine because we're doing retrospective analysis. Okay?
yeah. So
Do you want a microphone?
I think I'll try to speak loudly. So the one I recommend is probably from T4G X large to C whatever you want. Anything that's more smaller may takes even longer time, and we probably don't want to wait for hours in the tutorial. But yeah, anyways. I'll just choose probably this one. So reasonable size. And so you see that the number of CPUs and the runtime is not linearly correlated, because there are this baking oven process that that Ian shows on Monday. Like you can speed up the process by having more CPUs, but also there's some process you cannot speed up. For example, like we have data downloading in our workflow, and this always takes around 3 minutes or so to do that on the cloud. In our case, and even if you have more CPUs, you're not going to speed up this part. And there's also other like data reading and writing processes. So if you have more CPUs, you are going to have less runtime, but it's not linearly. Yeah, next we'll do, so we skip the key pair part. We don't choose any. And then we do select existing security group and use the default. So for the storage, just to be safe, we use 30 gigabytes here. We will not use up the whole thing, but just to be safe. And everyone with me? Good. Okay. And then next, we will launch the instance. And we choose proceed without key pair. And launch the instance. And you see I already successfully launched the instance here. And if I click on that instance, this is my instance that I just launched right now.
So, okay, so it's not there yet. I was up there yet. So where?
So whoever needs help, you can raise your hand, then someone will help you. How many of you are already here? Could you raise your hand? Right here? Okay, good. I'll just go next. So after you launch instance, you do connect. And you do connect. And you will see there's a pop-up of the terminal that you can use. So you're already connected to your instance here. Yeah. And so I'm just sending you the link to the tutorial notebook. You'll see something here, like here on the GitHub page, and it basically tell you how to run it on the cloud environment. So once you are already here, you have this a new terminal connecting to your instance. You can install first Docker using those commands. You can just copy and paste those commands here. And oh, okay. Everyone with me? Oh, yeah. You can scroll up. It's here. So those commands here. Oh. Yeah, yeah.
Okay.
Yeah, I'm just sending you. So you go to the instance and connect. You click on the instance you just create it and connect it. Everyone with me? No, okay, more time. So the tutorials, I already sent it in the Slack channel. So it's this one in the Slack channel. You can see those commands. Hmm? It's on Slack. I sent it on Slack. There's a Slack message I sent just now. Yeah, I'm on the instance and I already installed Docker. So if you already installed Docker successfully, you'll see a line saying Docker version 25 or something. That's meaning you are already doing everything right. So everything right? Hmm? Where's the mic? Do you see a mic somewhere? Yeah, so to open the terminal, you go to your instance and hit connect. Connect and you'll see the terminal. Good. The instructions is in the Slack channel.
Okay.
So you go to the Slack channel and there's a tutorial notebook, and then you install the Docker using those commands. You can just copy and paste there. And after you install Docker, you So how's everyone doing? Everyone with me? Or anyone, and Alex asked me, does anyone needs help? Raise their hand, or someone will go to help you. Everyone should be in the terminal and already install the Docker, right? Okay, I'll go next. So in the tutorial page, there's a commands to pull the Docker image. You want to do this one, sudo pull the Docker image and the latest tag. Be sure to use this one in the AWS cloud. So I just copy this command here and I will pull the container image.
The other ones. I can see they're not charged. So it's, you can walk in the room now and make
Okay.
everybody else.
So I already pull the container here
Okay.
in my terminal, and then I do the next command line here, the sudo docker run. And the running the same image, I just pulled the latest tag version. Yeah. So anyone has questions or? Yeah, so after you run the container, it will give you some link to the notebook, but you cannot just use this link. You need to copy paste it at some web browser, and then you go to your instance, and there's a public IPv4 DNS address. So you need to copy this address and go to that link. You replace the 127 whatever .1 with this address, and then you can open the notebook. So yeah, so you copy this link here, and you basically replace this part before the column, after the slash here, this address with the IP address here. So in your instance, this is the instance you have, and there's a public IPv4 DNS address. So you use this address, you copied it here, and you replace it with you replace the IP address in the link with the IPv4 DNS address of your instance, and then you open that in a new web browser tab.
Let's have a quick break. To forward the course, there is a new trick that we maybe have been working through recently. So let's do a quick break, maybe coffee time. And then we'll send a forward option that we have a vote that we can just in a couple of minutes.
Oh, okay.
Because otherwise,
I can give them the other way. Like you just need an. Oh, okay. It looks fine. Like they all reply.
No, they're not.
Okay,
All the way
okay.
in the back, they're not.
Yeah, let's take a break. And
Let's
if
take
you
a break.
if you have any questions, we're here to help.
When you remade the, so if you go online in the Jupyter book like this one,
Yeah.
that works because in maybe in the noise by one.
Like this one?
Mm,
No, the first noise file.
okay, so
This
yeah.
one?
This,
Mhm.
when you do the Docker run, see that line,
Mhm.
when you do Docker run,
Mhm.
you have to do the 88 blah, 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 column 8888. And then you have to do the minus IP, allow routes, all of that.
Okay,
All of that line needs to be on yours
okay,
because that's how they can open from the browser.
okay,
And the token is there as well. So
okay.
you would just have to update this line of code
Uh-huh.
into your,
I can send it on the Slack channel.
you could,
Yeah,
Yeah,
or I
yeah.
can update the notebook.
yeah, and it's okay if people to wait because some of them are still
Okay,
connecting.
okay. I thought it was easier. It was just a very
It's okay.
straightforward. I can.
It's only straightforward when we practice so much in a group.
I know. No, not this one. So I added this one with my GitHub. That's no, that's weird. Okay, that's fine. I'll try that first myself.
Yeah.
Just close it. Sudo docker run latest.
1 year.
No, that doesn't work. Or
This one that doesn't work.
this one? Probably I need to remove here. Cause it's on 2 lines that will be. Wait. This mess things up. No, I just start over. Probably I need that. Oh, no, that's, okay, I see what I mean. So they say that's 2 command. You need to
Okay, started with there.
work already located. Oh, I see.
I'm updating the page.
No, it says port already allocated, so I need to use a new port. Or I can. That's maybe.
Let me-
Yeah, sure. Maybe harder for them.
It's probably you're using it already. You're using it already. So for them, they're
What I
already-
can, I can do here is just simply clear up everything,
yes.
kill every Docker.
If we change the way we got
It is.
Which Docker is it? This one? This is already running? Why it doesn't allow me to?
Add a dash F after.
Okay, I need to force.
可以用导入法，可以用，我觉得没问题。
我先，哎，
随便，
哦，
直接用导入法，别的。
拼错了。可以吗？我得把这个也 Q 掉啊，它那个，哦，这是 image，不对，那我得重新 sudo docker pull 吧？不用吗？我直接 run 吗？直接 run 不，它这个是半行，哦，这好怪呀，等会儿。哎，这个吗？这个吗？
If you run another one, you run two.
Oh,
Just run.
oh, I see. 我怎么觉得这样更麻烦呢？
因为大家都已经装过一遍，所以就没有必要。
OK， 但它为啥打不开呢 ？Something wrong. Maybe because I run it 2 times.
直接把那个就有一个这个开放，放再开一点。
这算算气。哪个是我？这是我，我不要把别人的音色关了。没有人看到。
Another note on the cloud, if you get stuck and you feel like the instance is stuck, you can hit it, terminate it and start again. It's kind of like a marking step on your machine, but it's safe. Right, because we're all supposed to come here and everything, all put us once. So if you feel stuck, terminate, start again. It's very satisfying. I love it when you feel everything that's on the stuff. And it's fresh.
They're using a new way. They're using a new way to open that link and
I don't know if I've changed it.
yeah. But anyways,
I think I should just stay where you are. You shouldn't use this. Yeah, I think just do whatever you have already on the web page.
well, I mean that's much easier for me, but like Maria said they already used to this way.
Well,
I-
whoever had, yeah. Whoever is on the cloud now, just go back to the way we did it.
Yeah, I think just do whatever.
Oh, it doesn't finish it. Sorry.
How it works?
Yeah.
No, that's fine.
No, there's some weird bug. Is unable to find image. Oh.
No, the way we've been doing it here, but I'm able to run the notebook, but not link it to the browser using the LA.
Oh, yeah, that's.
I think that's the problem
That's
people are getting.
No, it's still starting. Did I do something wrong? You take over. I mean, I'm already used to how I did it before, and it's only
I know.
one step. But this is so different.
My understanding is pretty fragile. If you change one thing, I get
Yeah,
very.
we should change that here.
So how do you do it?
Well, we were using, I mean, it should work. I don't know why. The only thing about it is I'm using the key password.
You're using this 888 like previously. And we're still focusing on copy this IP address, paste it here, and add something here, right?
Oh, that's what we do.
No, that's not what I'm doing. So what I'm doing is just I copy this address. Wait, copy the wrong line. This one, I just copy this address. Put it here and copy this one and then replace from here to here. The new
same thing.
address. Yeah, that's the same thing.
Yeah, that's the same thing.
But you don't need to copy the token.
That's the same thing.
Yeah, that's already.
Yeah.
But like, what is the new way? Like, it didn't work.
Don't worry, don't ask me.
Okay, okay, okay. Anyway, so we'll just wait then.
You still have the old way?
Yeah, the old way here. I do not know how to run the new way.
Go into your-
Yeah, they just go to the tutorial page, tutorial notebook. That's just delete everything. Forget about the new way.
So who is running? Nobody.
Nobody? Where, where are you now? Like, I just wonder.
But like, again, what do you modify? Because now, right now, working and it didn't work.
Hold on a second. Can you open where you wanna be with the icons? That website?
This one?
Yeah.
This one?
Yeah, that's where everybody should be, right?
Yeah, that's where I should be.
Is anyone here?
No?
Nobody. Let's go back to the old way. The way you don't wanna.
Like a different image now, the no hub or something?
No, 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 just, you just use the old way, just use the link on the,
Okay.
on the tutorial page. Like the, pulling the latest version, running the latest version and replace that IP address with the IP address on EC3.
Same way you did it on the. Yeah. You increase the font.
Here,
Like, oh yeah, something.
even bigger.
People cannot read it. Oh yeah, that's good.
I already sent this link to the Slack channel so that they have their. I mean, I don't want to type them to type all those whole things, they can just copy paste.
Well, everybody was able to do this, right?
So-
Everybody was able to pull the Docker, pull the image.
Hold the Docker and then everyone run this one. Yeah, yeah. If you run it, it'll give you some link like that, right? Yeah, you don't open that link yet. So you copy that link and then you replace this part 127.0.0.1 with the IP address. You need to go to your EC2.
Oh, yes.
Yeah, the public. Okay, let me see.
So where is the structure? Yeah. So that's the issue. Maybe the key. Black people are right, they don't work, they, the ID card.
So I was right there. So I go back to my
Everybody, it must be confusing for many of us. So what we're gonna do is terminate your extent, coffee break, we'll resolve it, we'll start fresh after that. 10 minutes? All right, terminate your extent and then we'll start fresh. Everybody. Yeah. If you have it working, you don't have to terminate your extent.
Oh, sure, yeah. Yeah. Well, I feel it. But I believe it has a unique way. One thing is the quality. Yeah. Oh. Done, yeah. Yeah.
Everyone here already, like you have a notebook, the Jupyter Lab open? If you do not, raise your hand, then we'll help you. What happened? Wait, I lost connection. I need to connect, reconnect.
No problem. Good practice.
Okay. So if you are all here, let me make this larger. If you are all here in the Jupyter,
All right, sorry for the discussion, but I need to start again.
yeah. So if you are all here, you can just open this Jupyter notebook, this tutorial notebook, right here, the ML workflow face at class version. And if you open the notebook, like this one. So this is the same notebook that I just sent you by Slack with all the instructions and commands to pull and run the Docker. But like here we'll be running the notebook. This notebook start from downloading data to preparing all the input files, running FaceNet and running Gamma, and also running locations and cross correlations, and also double difference relocations. Anyways, this is just the notebook that's basically start from continuous waveform download to at the end you'll get a HypoDD relocated earthquake catalog. So what you can do here is just you do run and run all cells, and it will run the entire notebook. And depending on the type of instance you create, like the number of CPUs and the size of your instance, it could take different time. But like for this one, I would expect like I forgot which one I create, but it could be like something around 15 minutes or 20 minutes or so. So when it is running, I'll just walk you through those modules and what they do in the notebook. So you already done this part. So at the beginning, it's basically how you connect to the cloud and install Docker and pull the image, running the image. And after that, it's the tutorial of this catalog computation workflow. So there are links to those different modules we use. And if you want to see more details, or if you are trying to fine tune the parameters on another data set, you can refer to those links and look at their documentation. But we do have very brief comments here in this notebook to tell you what are parameters that you might want to change. Those are in highlighted colors. So in this notebook, we download 1 day data from the 2016 Central Italy sequence. So we choose 1 day from October the 18th, I believe. And the default parameters works for this 1 day data set, but like if you're going to apply it somewhere else, you need to be careful, and you probably need to change some of the parameters that we have here. So the first module downloads data from the arrays. When you're running this module, you basically you can see that it's requesting data with like using the OpsPy mass downloader function. So this is like a OpsPy package for Python. It's like a Python package for seismology modules, and it's basically, so here we actually have 130 stations, but just running we want a short demo, so we only choose the array stations, which it has like 25. But like if you want, you can just add the INGV network here, and then the network code and whatever channels or stations you like to. And also we do here from October the 18th to 19th, you can also change to another day. We just choose this day because it has some reasonable number of events that we can use to run, like say correlation or other type of measurement. But you can play with it by changing to another day, say for example. But here we will be downloading data from arrays. The waveforms are here in this waveform folder, and there's network and those stations. And there's 3 component waveform of 1 day long continuous waveforms. And after we download the waveform, we should take around 3 minutes or so. We will we run FaceNet for face peaking. So here in this notebook, we use the FaceNet Plus version, which is based on PyTorch, and also has functions predicting face peaks plus polarities and event labels. So this code block basically prepares the input file with all the path name of the waveform we just downloaded, and we also have a block to compute the station file in certain formats. It's basically converting the XML format to CSV format that required by FaceNet. And here, this command line runs the plus model of the FaceNet. So it's basically running the prediction function, and the model is FaceNet Plus. I think you can choose to be FaceNet or other versions of the FaceNet pre-trained models or anything that you can have. So to switch to another model. And then there's add polarity functions, and it gives you it gives you output of phase peaks and polarities. And after that, it gives the path, and you don't need to change that. All the paths are right. They're written in the previous code blocks, and yeah. Yeah, by the way, if you have local data, or if you like have data from others, you can include that data path when you are launching the container, so that you can get access to that data as well. But here we are running it on cloud, so we do it in this way. And after you, let me check. So after you download the data, we then run the gamma association. After you pick the data, we then run the gamma association. So this model takes the peaks, and there's an option to take the amplitude, but you can also turn that off as well. And there are some other parameters that you may want to change. for example, like the minimum number of picks required for each event in the association. There are also, you can also set the minimum number of P wave or S waves. That's also possible. And there's some other parameters like the dB scan EPS. So that's a parameter that is basically determines how large the window size to associate and the peaks into event. For example, if you have a very local network, you can use a smaller value. It's basically searching for peaks in a shorter window. But if you have a large network spanning over a large region, then the move out may have maybe more sparse in time, then you need to choose a larger number to include the later move out. So that's another parameter you may want to tune if you're working on other data sets of different scales. And there's another parameter called max sigma 11. So that's a parameter in the model that's basically tells you the threshold of the peak uncertainty. So for example, if there are some bad peaks in your database and you don't want to include them in association, say you want to remove all the outlier peaks, then you can choose a tighter value or something like. But this is basically depends on your peak qualities. You can try with different values. But I would suggest if you don't know anything about your data set yet, you just start from a larger value and look at the outputs. And if you see like a lot of mislinked or misassociated events, then you can decrease this uncertainty parameter to be like more precise in the peaks move out. Yeah, anyways, all of those configuration parameters are defined here. There are some others that might not be so important, or you can just leave them at default. But I think those are the three parameters that you may want to focus on when you are running your own test. And it also does some pre-processing on the data, on the station files and the peaks, and then and here it runs the gamma association, and after that it will be why is the downloading data take so long? Do we have good network connections? Oh, anyways, so so if everything runs well, you'll see the associate events in the gamma folder that we will be creating, and and next we use this associate event peaks to run hypo inverse to get an initial location. We need this step because when we are doing cross correlation, we need some reference to cut the window, and also on cross correlating the event pairs data. So we need an initial location from hypo inverse. We basically have functions who write in station file and also the phase peak files using our outputs, and this line runs the hypo inverse function. So there are parameter file in the hypo inverse folder. Which one is it? So yeah, this file. So you can look at the hypo inverse manual book to change any of those settings. For example, like reference depths at 0 or at 0 or something, or any weighting on the RMS or the distance. Anyways, I think you already probably use hypo inverse a lot, but like you can change those parameters here, and after that we will do hypo DD. Felix, you want to take over to give introductions to hypo DD?
Can I ask you something about FaceNet?
Yes, yes,
FaceNet is trained using data in California, right?
yes.
So how does it perform with like the earthquake in Italy, for example?
Yeah, that's a great question. So ideally, you want your training set and the test to have the same distribution, or like the same type of waveform or same type of event. So if you trained on local earthquake in Northern California and apply to something like here in this case, Italy with a local distance station, it will probably be fine. But if you're using the same model on say OBS data or something that's very different that have whale calls or others, then it might be problematic. So you need to either retrain your model or you need to do some pre-processing or post-processing. Yeah.
Thank you.
Does President allow training with local, like, with our own data or?
Yeah, sure. There's a training function for FaceNet as well. So if you want to retrain your model, I mean, like on the cloud, you can either load your already retrained model, like by just but you can just like including that your retrained model in the container and run it, change the model parameter to your new model. Or you can also do some retraining on the cloud. You just have your prepared data set, like the retrained data set with labels and waveforms, and then do the retraining here as well. Any other questions before we switch to HypoDD? That's weird. I shouldn't be. Oh no, I think it's
Who is running now? Who is running right now? The local.
Yeah.
so
The whole thing was about 20 minutes, right?
depending on the size of the
Yeah.
instance you choose. So mine is currently running FaceNet.
But you can track where it is. Right?
Yeah, we can get, yeah, now submitting in space.
Yeah, so
Everybody knows how to track where it's at. Okay. Who used FaceNet before?
yeah, a lot of them.
Higher. Who used I guess quick flow, right? With gamma and everything. Who used hyper inverse before? Okay. Who used hyper DD before?
HypoDD is the most.
So you all know that where you have to set those parameters depends on input file, input data. So as I said before, FaceNet produces consistent set of things. After them or not, another question. But that's every step of the inverse we need to check all of the law. Then that goes in. But now it is not down here. It's the same thing. We tailor it for this. Did you make me host? Oh. Yeah, hold on. I'm trying to get the share the screen, but I'm not. Uh, oh, you can show some slides. Good. Okay, now it's this and this, right? Is this good?
Yes, it's straight on top.
Okay, so where do you start? Is it still FaceNet running?
Yeah.
Okay. So once FaceNet is done, it will output pics, and then Gamma will associate those pics to earthquake events, and then that those associations will go into hyperinverse. Hyperinverse will generate a catalog. So you can use any locator. You can use a grid search. You can whatever you want. You just need an initial catalog. And when you do that, it's best to get the best catalog possible. So all those programs work on the basis of garbage in, garbage out. So don't think it's like you don't have to do anything to it's on automatic again. Okay, so it's slideshow. Oops, what? Shit. Is it good?
Yeah.
But it's going automatic, no? I cannot forward it. Oh, very slow. Anyway, so after every step, we need to make sure that the data that comes out is good and the data goes in is even better. Otherwise, at some point you're running, this is one day, but if you run, a couple of months, you will, wait for a couple of days. And if the first step wasn't successful, you will just wait most of the compute time. So as I said, the single event location are pretty straightforward to check because you have an event, you have a set of station, you can check on the pics and then look at the robustness of the location just based on the residuals, the formal errors of the location. Now, if you start relocating multiple events together, things get more complicated. For example, you relate events relative to each other. So if one event is really off, then it might bias the location of all other events too. So it's actually very difficult to track down errors in the data when you relocate multiple events at the same time. Well, there's a couple of checks that we can do to make sure that the results in the relocations are reasonable. So this is so HyperDD goes back to, I don't know, 25 years. I can't believe I'm giving a short introduction to this, but here I am. It's we're simply connecting hypercenters through differential time measurements at a common station. And on the left, you see single event location, which we use, for example, hypo-inverse. We use a face pix and then locate the events in space. And relative location, you took the difference in the arrival times and you relate that to the difference in the location. And so in this relative location system, you were able to minimize common mode model errors. And in a double difference location, you essentially you you spread a network of differential tile links across a large or multiple events and relocate them all at the same time. Now, those differential times you can get from in two ways. You can take the phase picks and form a difference for a given event at a common station, or you can use cross correlation to get very precise delay time measurements. Now, there's a difference between the two. The phase picks, they measure the nucleation point, and the correlation data measures the point of maximum moment release. Now, for small earthquakes, it's probably not a big deal, but when you get to magnitudes 2 or 3, then there's a difference because you don't necessarily have a circular rupture. But because the correlation data is often much better than the picks in terms of the precision, we want to take advantage of the correlation data. So this is just an example that shows I forgot how many seismograms, but like I think 200 aligned on the P-picks from a network in Northern California, and then at the bottom it's aligned on the S amplitude, and you can see how it cleans up all the shifts or all the errors in the P-picks. Now, I'll get to that later, but there's common misconceptions that once you have correlation data, you can get rid of the phase picks. You don't need them anymore because they're much better. But this is what I usually show, is that when you have 2 earthquakes observed at a bunch of stations at the surface, and you pick them, you pick the onsets, you can get very good onset picks for stations close to the pair. But as you go further out, your data gets noisier, and so your pick is less accurate. But you do get picks at all stations. Now, when you take this pair and get correlation data, you don't get any correlation data for stations above the events because they see different structure, and so they decorrelate very quickly. But for stations, in this case, for stations that are in direction of the event pair, you get a very good correlation measurements. And so it's very important to use those 2 data sets together. So you can use picks just on their own, but only in a few cases you can only use correlation data because of exactly that problem here, because the correlation data uses depth control in this particular case. So this is illustrated. It's actually from that manual in 2001. On the left side, you have an NCSN location, network locations. Then you relocate those using catalog data only, and you see that the main structure of the cluster stays the same and improves the resolution within the cluster. And then if you just use cross correlation data, the depth control collapses. But if you use both data sets together, you control the overall structure with the phase picks and the internal structure of the clusters with the correlation data. And so at the end, all that HyperDD does is trying to find the best, optimize the links between the different events and weights them depending on the quality and robustness of those links. So this is an example from the NASCAP, from the subduction zone in the NASCAP plate. And you see the red events are the ones that correlate, the blue events are the ones that didn't correlate. So you can string together all those earthquakes and relocate them relative to each other at the precision you have the data for. Now, another reason for using picks is, this is again going back to the central Italy sequence. You can see on the left side is a density plot of earthquakes, and on the right side is a density plot of correlated earthquakes. And you can see that north of the Sibillini thrust, which is the green line in the right figure, most earthquakes don't really correlate. And that's just something we're trying to figure out, but it's probably mostly through to complexity in the source and complexity in the structure. On the other hand, when you go south of the Sibillini thrust near L'Aquila, we have all those events that correlate very well, and they show very sharp structures. So that's why it's another reason why it's important to use PICs in combination with the correlation data to get the most complete image of seismicity. Yeah, so over those years, I heard many comments about hypo-DD, and it's some of the most prominent ones are, hypo-DD removes events, but hypo-DD does not remove events. So it does not relocate events that are ill-constrained to begin with. So if you put a lot of bad events in to relocate, it's not going to relocate them because they would influence the location of the good events. So, and of course, if you're trying to relocate one single event with no nearby events, then it's not going to work. So you need at least two events. Cross-correlation data replaces phase. I just made the case, I think. Then the velocity model is not important. That's not true because the velocity model links observations to the hypothetical parameters through the partial derivatives. So don't try to use a two-layer model with a sharp velocity contrast because the partials will just jump over that interface. It does not accept 3D models. No, it accepts homogeneous models, 1D models, and 3D BNS wave velocity models. So I used to give a workshop that over 3 days and not 3 hours or 10 minutes. And I pulled some of the slides from that workshop, and there's a lot of do's and don'ts, and I just picked the one that are most important, I think, when generating earthquake catalogs or any kind of data processing. So always look at the data. So when you have your set of PICs and when you have your set of cross-correlation data, an easy way to see whether they're consistent is to compare those differential data together. So in this case, you can see that when you look at the highest correlated seismograms and differential times, you can see, and you compare them to the big PICs, you actually see the uncertainty in the PICs. And here, I think 20 milliseconds, but for 70 milliseconds for the P waves, and then 30 milliseconds for the S wave. So those histograms should look very reasonable. So sometimes you would see bimodular or trimodular distributions, the cross-correlation data, which simply means you have cycle skipping. So you skipped when you cross-correlate, you didn't correlate on the first amplitude on the first wiggle, but on the second or the third. So very easy way to look whether this is something that can go into the inversion, or you can just use all those data separately. So you use the PICs alone, the S PICs alone, the cross-correlation P PICs alone, and the cross-correlation S alone, and you should get more or less the same structure, depending on the accuracy. So for example, the PICs here, you see that obviously they're more distributed because the PICs are not as accurate as the correlation data. Choose an appropriate model. Yeah, don't choose a two-layer model. Just use something that's reasonable. So that's, for example, for Parkfield. If you want to use a 1D model, something on the right is probably most appropriate because we all know that the velocity increases with depth and it's not a step function. And then you can recover structures that for example, we generated synthetics through a 3D model and then relocated them with the 1D model, and you can see a pretty good match in those circles. Evaluate results. Once you have a catalog and you use it for interpretation, you have to make sure that the structures you interpret are also resolvable. So this is from an example on the East Pacific Rise, where we imaged a fluid circulation cell, and we had a downgoing pipe over here. And of course, with the few stations we had to make sure that we actually able to image that pipe because it was all important for our interpretation on what's happening on that section of the East Pacific Rise. And the simple way to do that is you generate synthetics. You generate a pipe on the left, you add noise to the data and the locations, and then you relocate them and you see whether where can you resolve the pipe and where it's more diffuse. I think those are the yeah, so that's just but those are essentially common approaches for any kind of data analysis. It's just important that we do this here and not start with running the notebook and then looking at the results without even thinking twice whether they make sense or not. Where are we with running the notebook? All done? Is done?
Yeah.
Oh,
This will be opening
Yeah, so you can find out, right? Yeah, right.
Yeah, depending on the level of concern you choose, you may either feel on freestyle or you already have everything down. So, yeah, if everything goes well, at the end, you'll see the clock.
pero con no hacer conexión. Bien, bien. Bueno, no te corre nada. Ah, bien.
Okay, there's a question on Zoom. And it's actually another common misconception, which I don't see in my list. The clustering. So hyper-DD doesn't cluster. And it clusters, at least not in a physical sense. It doesn't find, clusters of earthquakes that have some physical relationship. When it clusters, it's simply because you choose, like, by defining the parameters, you define it. You choose that cluster. So they cluster only by the strength of the links between the events. So if that is very, very high in your application, then you very likely end up with multiple clusters because they're not linked together strong enough. But that's your choice. But at the end, every earthquake needs to have 4 stations for a location. And so if you choose 10 in a relative location scheme, then you split this up for all the events that don't have that station. So those are all. So for those who used HyperDD before, who read the manual? I don't know, nobody. Oh, you did? Thank you. So yes, there's a manual that comes with the software, and usually that's the first thing. I try to keep it short. That was a long time ago. But anyway, so part of this exercise here is to automatically find parameters that of the benchmarks for whatever common side of the type of inverse or dominant log or whatever. Do some type of analysis that you can do, or diagnostic tools that you can run.
I think they're all good. I'll just,
It all ran.
yeah. Do you want to show them the,
Good job.
yeah, okay.
You finished? Yeah. Oh.
I must have had a good conversation.
Nice. Is it Perry tonight?
Yeah, definitely Mexico.
So this is my notebook, and I think I've finished running everything here already. And you can look at the results. So in my case, I downloaded the data, which takes quite a long time, probably costs a lot of people. Oh, excuse me. And then you, good. So, yeah, it takes longer than I thought because probably there's a lot of requests coming from us downloading the data. And so that's slower, that's possible. And also, that's FaceNet, and you can check how long it takes here. So, sorry, wrong notebook. No. This is my notebook, sorry. Oh, I lost connection. Okay. Good. Okay. So this is my notebook, and you can check. The data is there, and that's the FaceNet. It takes about 8 minutes. In my Amazon instance, I choose the C6 whatever version, and with 33 CPUs, and so it takes around 8 minutes. So I think some of you chose the X2 large, the T4, and it takes around like 20 something minutes. So you can sort of see the difference in the running time. And also the gamma here, you can see the runtime. That's the runtime. So I do have a 32 CPU instance, so it's using 31 for running the job. And you see that it takes less than 1 minute in my case. I think if you choose a T4 2X large, that will take around 3 minutes or so. And that's a hypo-inverse. It almost takes no time to run it. And that's the output of hypo-inverse if you're familiar with the program. And I'm also plotting the hypo-inverse results. So those are the locations, location output of the hypo-inverse locations. And we use this location to generate input to HypoDD files. We need a face file, and we need a DT file, and we need a we need the CC file. So this is converting the format to the face file using the hypo-inverse locations. And the next module is called course correlation time. So it's the code from David Schaff, and he it's basically a mixture of C code, Fortran code, and shell scripts. Basically, it's very efficient, but it's kind of designed for certain data sets. So if you want to apply it somewhere else, you probably need to change some of the parameters in those code. For example, like the window length for PNS waves, and also the function to calculate theoretical travel time when you don't have a peak on a certain channel. Yeah, so the source code are in the container. Yeah, in the CC folder in the container. So there's a lot of source code available. So you may need to change those code, and so that it's kind of fits better your data. But here we just we cut the waveform based on the hypo-inverse locations and calculated travel time windows based on that. And then we calculate the travel time, the correlation delay time measurements. So we need to give it a face file that is used to calculate the delay time between event pairs. And there's certain commands to run the correlation. Yeah, so you can probably ignore those warning or error messages, but like those correlation measurements will be here in this Coral folder. And next we have a script to convert from those correlation measurements, which is like binary files, to the HypoDD input format, the DTCC file. So it's a shell script that converts the format. You need to give it the directory where you have the CC output and also the face file. And sorry, just to say that if you use the same face file for delay time measurement and also for the course correlation calculation, like we did, like what we do here in this notebook, you just you can ignore this input. And after that, we run HypoDD. So this is runs the functions of HypoDD that prepares the DT files from the face file, and we also give it the path to the CC files we just created. And here for HypoDD, the parameter file is here in the HypoDD results folder. And if you are working on other data set, you might want to change those parameters because they are specially designed for this test data set. They may not be working perfectly on any other data sets. You may get something I don't know, it's not that perfect. but like here after running the HypoDD, we plot the event locations. So this is the final catalog output we get. I'm plotting in blue the hypo-inverse locations and in orange color the HypoDD locations. So you sort of see there are some dense, very dense clusters and have some structures in there. That's only one day data, and you can scale this up to even larger data sets on the AWS cloud. So actually, I have talked to some of you, and some of you didn't have things running well. The reason could be either you do not have that many resources. I know some of you started the instance with too small size to host this whole thing because it runs one day continuous data. So if you have a tiny instance, it probably won't have enough resources to run. So it may give you some weird error. And also there's some people have tried to run it locally on their machine. So if you do not have, for example, like my instance has 32 CPUs, but that's not that common for your local machine. So if your local machine do not have that many resources, it may break at some point, like because there are not that many CPUs available or memories available for this. So yeah, that's where cloud comes in. Like you can create a larger instance if you have a larger data set. And there's no limit, like for your local machine, you need to buy new chips or new machines. That's makes it's possible to run large scale data. And yeah, that's it. Our final product is like a double difference relocated catalog. And after that, you may use this catalog for later processing. I think Teresa will use this catalog for unsupervised machine learning in the afternoon session. So can stay here to hear more from her. And you have anything else? Thank you.
Some of the modules here were finished yesterday. I'd like to thank David for fixing some of the problems. But this is work in progress and there will be a streamline. Yes.
I couldn't help notice how many different file formats you have.
Yeah, I kind of thought when you started talking about the correlation data, we formatted the HypoDD input. So when we do, I mean, yeah, that's quite a few.
It's got to be a barrier for anybody actually using it.
Well, the issues, for example, the biggest problem is the correlation data. For one day it's fine, but it's station based because you correlate at the station, but when you do the relocation, you need a pairwise. So you have to convert it from station based to pairwise, and then you have to do sort of, put everything together, tie everything together PNS to get into. But I hear you. There's room for improvement.
Well, one of the things I'm talking about is when I talk about the past. One of the things I've always this MongoDB database here, I'll talk about this afternoon, but it is a fabulous way to avoid a lot of data format problems.
Yeah.
Once you master it, because it's actually any tabular data that you can rearrange it in the database incredibly easy. So a lot of things that are really hard to do with the file can become a lot easier if you use a database. So that's just a suggestion.
Yeah.
It's got to be a nightmare to run. It's
So,
really amazing piece of work.
you think about databases, for many years. The issue is with those 10 billion correlation measurements. We need to access them efficiently, but I can't get answers because even waveforms, because I know exactly where that file is. I can that code. I can access that file like in real time. I don't have to go through some, all of it.
There's some tricks about using database.
Yeah, right.
It was a comment basically because this has got to be really difficult to set up.
But if it's fast and if it's hidden, it needs, a notebook, then nobody really cares.
And also is the blue piece, this is a really great illustration of that. A complex mix of research code that's mixed together to make a coherent
Yeah.
processing workflow.
Yeah, so if you check the Docker file, there's Python code, there's a C code, there's Fortran code, there's all these others. So that's probably a nice example. If you want to containerize your own code, you may find something similar that you can just use that. Okay, I think it's time for lunch.
unmute. So I think people on Zoom should be hearing and seeing me. I can't see the chat right now, but hopefully somebody will let me know if that's not the case. Let's see here. Sure how to get rid of that. Go away. All right. Well, as the title conveys here, today we're going to be talking about unsupervised machine learning for seismology. We spent the first half of today looking at supervised methods for phase picking and association. And so all of those methods are based on models that are trained on, in these cases, hundreds of thousands of phase picks and associations. And in that way, we're able to train the model to recognize similar patterns. However, unsupervised machine learning does not require hundreds of thousands or any labeled data to do its analysis. It simply infers patterns within the existing data set. So that's kind of the difference between this morning session and this afternoon session. And yeah, my name is Teresa Sowie. I'm currently a postdoc at the USGS, but I'm going to be talking about the thesis work that I did at Lamont Doherty for today's lecture. Okay, so first we're going to talk a little bit about what unsupervised machine learning is, and then we're going to do the tutorial, which involves actually the same data set or a subset of the same data set that we used in this morning's exercise. That is the Italy Amatrice 2016 earthquake sequence. Okay, so like I said before, when we're thinking about supervised machine learning, we can do the old classic cats and dogs example. And so in this case, we have a human here who has a pile of pictures of cats and dogs, and they've gone through and labeled each of them accordingly. And then we have a new data set that we want to be sorted. We don't know which ones are cats and which ones are dogs, right? And so we train a model to extract some features. What features those are, that depends on the model. And then we recognize which features are associated with which labels, with which probabilities. We then look at those features for the new data set and assign those new data to their proper classification. And so at the end, you've got two classes, cats and dogs, and your new data is sorted. However, for unsupervised machine learning, we can kind of think about it like an alien looking at our new data set. It doesn't know what a cat is or what a dog is, but it's still going to try to extract some features and then infer different groups of animals or whatever they are into their separate clusters if you are using a clustering algorithm. And so in this case, we would need a human to go after the fact and interpret those clusters and maybe do some ground truthing to make sure that your results are something that's scientifically meaningful. And so put in a bit more mathematical terms, we can describe supervised machine learning as training a function that best approximates mapping between the input data X and the labels Y, shown here, f of X equals Y. And we're learning this function that best performs that mapping operation. And so we've seen examples of this today, where our function is trained on millions of P and S wave arrivals. So we have our input waveforms, we're extracting features in this part here, and then we're using a fully connected neural network to assign class probabilities, if it's a P wave, an S wave, or noise. However, for unsupervised machine learning, we're going to be learning a function that infers natural structure within the data. And so we don't actually have our labels. Why? We're going to be learning those as well. And so there's pros and cons for each of these two flavors of machine learning. Supervised, you need labeled data sets. It only finds patterns that it has already learned. And it's good, as we've seen here, for routine work, things where we kind of expect and are able to evaluate the outcome. For unsupervised machine learning, we need unlabeled data. It infers general patterns within the data set, and it's good for exploratory work. If you don't know what you're looking for, but you want to get an overall sense of what your data holds, this might be a better method or complementary method. Unsupervised machine learning is much less utilized in seismology than supervised machine learning. Here we have a plot showing the cumulative number of papers from about 1993 to 2022. And we can see that the number of supervised deep learning papers is accelerating over time, whereas the unsupervised deep learning is increasing at a slower rate. And so part of the reason for this is, well, like I said before, interpreting and analyzing the results from unsupervised machine learning is not as cut and dry. You're not necessarily going to have a precision or an accuracy because you don't know what classes you're aiming for. And so here's some examples of commonly used unsupervised and supervised machine learning. I won't go over all of these, but we do have dimensionality reduction. So that's where we take something that's high dimensionality and reduce it into a smaller object in a clever way that still contains the important information that we care about. Maybe we're just removing sparse data, things like that. We also have clustering algorithms. So I've kind of combined dimensionality and reduction and clustering up until this point, but they're actually two very separate things. Clustering is where you're going to take your data, whether it's already been reduced in dimensionality or not, and then infer families within that data. Okay, and then supervised machine learning, there's regression or classification, and these are some of the more common algorithms, but we're not going to be talking about that today. So let's go over a couple of examples about feature extraction and dimensionality reduction. So from a broad sense, we're trying to extract meaningful features from our data before we use it in an analysis based on the principle of garbage in, garbage out. And so in this figure here, we can see strain data over time in a lab stick slip experiment. And it's very noisy. However, there are these kind of peaks appearing here. Now, we could just put this into some kind of machine learning algorithm, but better is that we extract some of the more important features that will convey some of the science that we're trying to explore. And so in this case, these authors have calculated the variance, kurtosis, and some kind of threshold. And you can see now the data are much cleaner, and these are going to be more appropriate data streams to use in machine learning. And so there's all sorts of benefits of reducing the dimensionality of your data. You reduce noise and thus overfitting from your model. It can aid interpretation, so get you closer to the scientific question that you're trying to approach. It does reduce the dimensionality, which is going to be improving your calculations because of what's called the cursive dimensionality, which is to say that if you're calculating distances between very large dimensionality, say like a 300 dimension objects, and you're doing a Euclidean distance, that distance is going to be inflated compared to if you had, say, a two-dimensional object that has a similar kind of distance, just by nature of having so many more dimensions. And because your data are now smaller, you'll have faster computations. There's a ton of dimensionality reduction and feature extraction techniques, and they will depend on your data type and domain knowledge. Just a kind of depiction of what dimensionality reduction and feature extraction might look like. For example, we may want to find the features with the highest variance or spread. And so if we have a two-dimensional data set here and we want to cluster it, we want to make sure the features that we're pulling out are going to separate these data in a smart way. And so our original data are these green points here, and then we can either project them onto the A-axis or on the B-axis. We can see if we project them onto the B-axis, we are losing a dimension there, but we're actually condensing our data so that they're even closer together. But if we project it onto the A-axis and we're bringing just all of these points down here, we can see that there's a bit more spread in the data that, of course, exists in the original data set, but we don't need this B-axis in order to express those kinds of structure. And so we can safely get rid of the B dimension and reduce it so it's just one dimension, and we still keep the important information. So that's a really like high level kind of conceptual idea of why we're doing dimensionality reduction and feature extraction. Here's a more complicated example. So this is called non-negative matrix factorization, and we're actually going to be using it in a few minutes for our algorithm tutorial. And so what we have here what we began with was a data set of faces that looks like this. And we've trained a model to extract only the most important features that help discern these faces. And so if there's a feature that's in every single face, maybe like whatever, a bit of whiteness in the eyebrow area here, that feature won't be extracted because it's not helping you characterize the different data. However, things like where the nose and eyes are, so those are being extracted here. This is a parts-based representation. If you ever, this happened to me the other day, I saw a scooter on the side of the street and I thought it was like a pair of dumbbells like this. And that's because I saw these two circles and a line connecting it. In my head, I was like, that kind of looks like a set of dumbbells, but in fact, it was a scooter, which makes a lot more sense. That's kind of how this learning representation, that's basically what it's modeling. You look at specific shapes and then you add them together and you try and get an image composed out of it. And so it's non-negative because our input data needs to be only positive. And that's useful because compared to other similar kind of parts-based representations like this, we're only additive and it's going to make it easier to interpret in the end. And so in this case, we've now learned a dictionary of different facial features. You can pick them out a little bit here, eyebrows, there's a nose shadow, and then a weighting matrix that when you multiply them, each one of these features will be weighted according to the darkness of this matrix here, and then you'll be able to recompose the original figure. Now this dictionary of facial features is the same for the entire data set of faces, but these weighting matrices differ for each face. And so in a way, you've been able to reduce this face into simply a weighting matrix. And then you have your dictionary, which it's weighted by. So we're going to revisit this example in a seismic context in a little bit. Just kidding, we're going to do it right now. And so I'm going to introduce you now to the algorithm that we'll be focusing on today. It's spectral unsupervised feature extraction, otherwise known as SpecUFEX. So it's developed by Ben Holtzman et al. In 2018. And so in this case, we're not going to be learning a set of faces. We're going to be learning a set of spectrograms. And so we've got a pile of spectrograms right here, frequency through time. They're showing different earthquakes from a sequence. And now we've trained a model to reduce them into the product of a dictionary and an activation coefficient matrix, or ACM. And so this dictionary has now reduced the different frequency contents into spectral patterns. These patterns look like normal distributions that are centered over a frequency band. And this makes sense in a dimensionality reduction framework, because if you imagine your spectrogram and you've got, say, a bright element at around 10 hertz, you're not just going to see an element at 10 hertz. You'll see something at 10.1, 10.2, 9.9. It's not appearing just by itself. And so you can model what are the most common and most strong frequency bands in here, and then sort them out so that you have each of these bands not overlapping with each other too much. They're capturing the main frequency content, and then to express that content over time, we multiply it by what is essentially a weighting matrix. So when we multiply these two, we get something that resembles the original spectrogram. And so we have a dictionary for the entire data set, and then for each spectrogram, it gets its own weighting matrix, its own activation coefficient matrix. And similar with the faces, if there is some kind of frequency pattern that doesn't discriminate these events from each other at all, for example, you've got a 25 hertz ring throughout, because of the instrument or something, it'll remove that because there's nothing to be learned from that information. And so let's talk a little bit about clustering now. Say you've done your dimensionality reduction. Maybe it's just statistical measures of your waveform, the mean, the variance, or maybe it's something more complicated like non-negative matrix factorization. But in any case, you want to cluster your data now to get an idea of the overall structure or groups of similar waveforms. There are so many clustering algorithms. I can't go over them all today. I couldn't even if I wanted to, but here is a list sorry, this link is kind of hidden here, but it's from the scikit-learn package, where we have each row is a different data set. You can see they have a natural structure, and we can see, looking at these 2D data, what the structure should be. And so we can compare these different columns, which are different clustering algorithms, and see which one might be best for a given data set. And so we have agglomerative clustering. That's their word for hierarchical clustering. We'll be talking a little bit about that one. Gaussian mixture models, those are used in the gamma algorithm, if I'm not mistaken. And there's just spectral clustering is actually a version of k-means clustering, which we'll talk about now. But yeah, again, based on your domain knowledge, based on your data set, you're going to want to choose your clustering algorithm accordingly, or maybe just try a lot of them and see what works best. So let's talk about the simplest, most kind of baseline clustering algorithm. This is a great one to choose just out of the gate to see if there's any really strong clusters in your data. So let's say we've got two-dimensional data points here. What we're going to do is choose a number of clusters. That's a user-chosen parameter. In this case, we choose 2. And so we initiate cluster centroids randomly based on existing data points. I've just put them here and here. Now we're going to assign each of these dots to their closest centroid, just using Euclidean distances or whatever distance you want. And then we're going to calculate the cluster centroid properly. So now it'll be kind of the center of mass of these 2 groups. So it'll be around here and around here. And those are actually the only 2 steps. You're going to reassign the dots according to their closest centroid. So now these guys are in this green cluster, and then you're going to recalculate the centroids. And you keep doing that until you reach a point of stability, or the difference between the centroids moving is below a certain threshold, which you can also set. And at the end, what you have is 2 clusters that hopefully are kind of intuitive in terms of where their assignments are. I will say some of the bad parts about k-means clustering is if you've got really globular data, it'll just kind of cut it like a pizza slice. Like if there's not a lot of structure, it'll just draw lines to divide the 2 sections. And so this example here does kind of have 2 discrete clusters, but we'll see in real data quite often that's not the case. So here's another, oh yeah, question. Yeah, so that's a good question. I'll show later how we can basically sweep number of clusters from say 2 to 20 and try to evaluate the strength of clustering there. Yeah. But this is part of the challenge of unsupervised machine learning is we don't really know what the answer is beforehand. Okay, so let's talk about another clustering algorithm. This one's also very common. It's called hierarchical clustering, and we'll be using a distance metric known as single link, or a distance method known as single linkage. And so on the left-hand side here, we can see a similar plot to what we had before. It's 2-dimensional data. We've just got a few data points that we're interested in clustering. And then on the right-hand side, we have what's going to be called a dendrogram. This is going to track the hierarchical steps throughout the clustering process. And so we begin with 6 data points and 6 separate clusters. We're then going to have 5 clusters. And how do we do that? Well, we're just going to join the 2 closest neighboring data points, and we can see that I used to have a mouse. What happened to it? Well, anyway, we can see on the right-hand side that we've now joined 2 of the closest data points, and our distance that we're allowing for under a certain distance, we're going to be joining these data points together. Above a certain distance, they're going to be in their own clusters. And so that's this dashed line, green line that's going up here. That's going to be showing as we increase the amount of distance that's allowed for clusters to form. So now we've joined the next the next closest clusters, and we're going to recalculate our distance matrix and join the closest ones again. We can see our dendrogram is now growing as we connect more branches. However, we're still containing the hierarchical structure that is kind of the history of our clustering. We can see at the bottom the data points that are underneath the same branches. They're most similar to each other than other data points. So we'll just keep on going. We'll join those two now that our distance threshold is much bigger. And then finally, you can join them all until they're just one cluster. So between all of them being their own discrete cluster and all of them being one cluster, those two end members obviously aren't very useful. But the idea with the dendrogram is then you can then look at your structure of the data and try and choose a split point that makes sense. It's a little hard to see in this example, but sometimes you can see that there's a point where there's clearly different branches appearing to kind of hint to you that there's, say, different like overall structure to your data. Okay. And so, yeah, when you choose your dendrograms, this is another way of viewing it. We can see at the top, our dendrogram, as the distance threshold increases, we're bringing that green line upwards. And then in the bottom plot, we can see how the number of clusters decreases as we increase that distance matrix. Okay, and then a good question was, how do we choose the number of clusters? So you can kind of take what we might call a semi-supervised approach. Maybe you do have an idea of what you're looking for. For example, this is an example from repeating earthquake sequences on the San Andreas Fault. And so we actually had a criteria for what our clusters should be. They should be co-located, very similar waveforms, blah, blah, blah. And so that red line is showing the number of critical events that we were able to pull out from the clusters for a given number of clusters. And so that's one way you can optimize it, is a kind of semi-supervised approach where you do have a target. But in case that's not, many times that's not the case, and you just want to have an idea of what number of clusters might be a good starting point. And so for that, we're going to be using silhouette scores. So this is the ratio of the average distance of a given, let me start over. So each point in a cluster is going to be is going to have a silhouette score calculated for it. And so if you want to get an idea of the score of your entire clustering set, you take the average of that score. What is the silhouette score? So it's going to be a ratio of how close or how far a single data point is from every data point in the closest neighboring cluster over the what is the distance of that data point to every data point in its cluster. And so if we have a well-clustered data point, it'll be really far from all of the other clusters and really close to all the data in its own cluster. That's how we say it's well clustered. And so this silhouette score is going to go between -1 and 1, where 1 is a very well clustered data point. It is very close to everything in its assigned cluster. It's very far from all the other clusters, or the closest neighboring cluster, to be more precise. So yeah, in this example, we've calculated between 2 and 10 clusters, calculated the silhouette score for each of those scenarios for each data point, taken the average, and that's what's showing right here is the mean silhouette score for a given number of clusters. And in this example, we found that 6 clusters gave the best silhouette score. That doesn't mean that's the only answer. This is just a good answer to start with. And so in summary, for the unsupervised machine learning part of this talk, unsupervised ML infers patterns in large data sets without the need for prior training labels. And feature extraction and dimensionality reduction are integral to this process. They can add clustering, aid clustering and interpretation. They reduce your computational time. And some of these algorithms are just kind of are not going to work if your data are too high dimension. Some examples of the algorithms I talked about were non-negative matrix factorization, k-means clustering, and hierarchical clustering. Okay, so I'm going to talk a little bit about the specific algorithm we'll be looking at today. It's called SPECUFEX. This is short for spectral unsupervised feature extraction. We can see a workflow here showing the algorithm. And so we're going to start with waveforms. We transform them into spectrograms. We already talked about non-negative matrix factorization. And so essentially we decompose these into a dictionary that's shared for all of the spectrograms and activation coefficient matrices, or ACM, which are unique for each spectrogram. We actually throw the dictionary out at this point, and we're only going to be using these reduced dimensionality ACMs. What's cool about these ACMs is we can see that they kind of resemble the original spectrogram, but at a lower resolution. We haven't just decimated in time and frequency. We've actually lowered the resolution in a clever way that's retaining the important time varying spectral content. And so we throw out the dictionary. All we have is now a pile of these ACMs. And what we're going to do is use those as input into a hidden Markov model, and then convert those into fingerprints. And then we're going to use k-means clustering to cluster those fingerprints. Let's break down those steps a little bit slower. Okay, so when we generate a spectrogram, this may seem like the most simple part of the process, probably something that a lot of us have done before. However, because this is our input data, it's really important that we choose the parameters carefully for calculating our spectrogram. And so we know that a spectrogram is just a series of short time Fourier transforms. And so each of these columns is a time step. It's a window in which the waveform is now calculated into a spectrum and then shown through time. And so each one of these columns is basically like an input into the machine learning algorithm. So we need to make sure each one of those columns has the information that we're curious about. So basically you need to make sure that if you have a low frequency constraint, you want to get down to a certain frequency, you need to make sure your time windows are long enough to capture that frequency. However, as we'll see in a little bit, you also need resolution through time, not just for the obvious reason that you'll be losing structure if you're averaging over too long of a window, but also you need a certain number of time steps in order for the hidden Markov model to work. That is, if we're learning things through time, you need a certain number. And in our experiments, we find that 20. You need about 20 time steps at least to get the algorithm working. So that's two kind of end member constraints. You want the windows to be long enough to capture your low frequency energy. You want them to be short enough so that you can have, 20 or more windows in a segment. And so we're using 20-second windows here. And so that helps us reach that criteria. Anything else? Okay, non-negative matrix factorization. We already talked about this. We're extracting spectral patterns, that is frequency distributions through time. Like I said, we throw out the dictionary, and then all we have is our activation coefficient matrices. And we're going to model these as a hidden Markov process. In a hidden Markov process, you're looking at states through time, which are controlling your observations. And those states follow each other in just a concurrent fashion, meaning that you don't have memory of the 10 states that happened before. You only remember the state that happened right before. And so each state is going to control the probability of the next state, so on and so forth. And then there's also a probability that each of those states emits a certain observation. I know this is kind of coded language here, but in this case, our observations are our frequency patterns, and the hidden states are just that. And so we see which states are controlling which patterns of spectral patterns that we learned in the previous step, and then how those states evolve through time. The interesting thing about this example is you can actually still see some of the original waveform structure in this state sequence matrix. For example, a little bit of noise before, a little bit of noise afterwards, and then in the middle where the waveform's happening, there's things are kind of going up and down. The order of these states doesn't really matter, but we can see, at least relatively speaking, there's kind of nothing and then something and then back to nothing. And so we're almost done with the SpecEffects algorithm. We're going to take this state sequence matrix and actually count the transitions from one state to another. And so in this way, we're getting the kind of time varying nature of this object. So for example, like I said, we've got this kind of noisy section here that looks like about state 10 or so. There's 15 states here. And we can see that state 10 is repeating it after itself. It's going from state 10 to state 10, over here, state 10 to state 10, state 10. And we can see here at the element 1010 on the fingerprint that there's a bright spot. Meanwhile, if we have something here where we're going from 5 to 1 to 5 to 6, those are going to be off diagonal. So if it goes from 5 to 1, you'll be at element 5-1, so on and so forth. And so, like I said, there are 15 states. That's actually a user chosen parameter, but 15 seems like it works for most cases. And so this fingerprint is actually just 15 by 15 elements. So just 255 elements in this data object. And yet we reduced it from a spectrogram that had, sampling rate of 1,000 samples per second. It's 20 seconds long. It's got frequency bins, maybe 100 frequency bins. So we're taking this very large dimensionality object and then shrinking it down to something while still containing the important time varying frequency aspects of it. So SpecEffects, although a relatively new algorithm, we do have a few publications showing its utility. So in this case, we're applying it to ice quakes at an alpine glacier. And so we can see one of the dimensionality reduction techniques that's very common actually is PCA. I didn't talk about it here, but it is essentially trying to increase the variance in your data set and projecting it onto different axes in order to do that. And so we've performed PCA on the fingerprints. We're plotting the first 3 principal components, and we can see that there's, structure arising from these data. There's this kind of triangular pyramidal shape here. We used our silhouette scores. Remember, we calculated that for each data point to see how well clustered they are. And so this is also a good way to get the best clustered data points in your cluster. We can see that the lines between these clusters are kind of blurred. This was the pizza cutting problem that I mentioned for k-means clustering, which we're using here. And so if we want to analyze the contents of these clusters, we probably don't want to pick data points that are at these borders. Like maybe eventually we'll want to see what's at the borders, but right now we're just trying to ascertain what the overall differences in the data set are. And so we're going to take these points. There's 50 X's for each of the 3 clusters, and those are the 50 points with the highest silhouette scores. And so we can see they're kind of away from the middle of the clusters. They're like the best clustered data. When we plot those, so we're going to rewind the tape. These were fingerprints that we clustered here, but they are each associated with a waveform. So now we're taking those associated waveforms, we're lining them up in time, because before they were just kind of arriving anywhere. And so we've lined them up in time in order to see the coherency between these various wiggles. We can see there's a lot of subtle structure that's found in these 3 clusters. For example, there's some coda ringing here. That's coherent between these waveforms. I think there's actually, sorry, I said 50, there's just 20, but yeah, so these 20 waveforms, there's high coherency between them. You can see the this arrival here is unique for each of the clusters. And so this is how you could start to get a really broad sense of some of the families in your data. This would also be a great first step for template matching if you don't know what templates to use. So you could pick the highest silhouette scores and use them as a template. Yes?
Do you have correlation to with the location of the station where that data was measured? Because
Yeah, so they're, obviously, these are all coming from one station. There's no distance information that's being used right now, but, and what, this paper does talk about the locations. They're not necessarily like co-located. So that's kind of another interesting, feature is like these red ones, they peer along a crack. But the orange ones are kind of everywhere. Yeah. Yeah, so this is all a single station technique. Yeah. Yeah. And we did a similar method for repeating earthquakes on the San Andreas Fault. But in this case, we used hierarchical clustering on the fingerprints and basically kept the distance threshold so small that we ended up with many, many clusters of very similar earthquakes, which we could then see if they were co-located, had similar magnitudes, and possibly be repeating earthquakes that were missed in the original catalog because of possibly inaccurate locations, missing waveforms, and some other reasons that I won't go into now. But so we can see here in blue are repeating earthquakes from sequences that were already known. And in red, we're repeating earthquakes that were found through this study. And so we can see, for example, you might have a sequence, but then one earthquake is a little bit off. And so you lose that in your location criteria because it's too far away. It's not overlapping. However, because we're using hierarchical clustering of fingerprints, we're actually clustering similarity independent of location. And so you're not dependent on super accurate catalog locations in order to find these overlapping events. You can find highly similar overlapping events without calculating cross-correlation coefficients for every pair, and then see that they're repeating earthquake sequences. So just a couple of examples of the utility of SpecUFX. Today we're going to be looking at a subset of the Amatrice sequence. So Felix and Kaiwen talked about this sequence already in 2016. We're going to be looking at 6 days of data, and within those 6 days, only 1,000 earthquakes. That's just to keep the tutorial lightweight. And so the broad strokes workflow is going to be, we're going to take earthquake waveforms, calculate spectrograms, convert them into fingerprints, then do k-means clustering evaluated with silhouette scores. I'll show some of the preliminary results, although this was from an earlier version, so you'll probably be getting slightly different results. But yeah, so 1,000 earthquakes. We've now, we've clustered them in fingerprint space, but now we're coloring those cluster assignments by cluster assignment and then plotting them in map view. And so we can see any kind of spatial patterns that appear in the clustering. I did this for k=3 clusters, but I've removed the second cluster, and you'll see why. You can begin to see a little bit of structure. This is, again, single station, single component. And so you definitely would want to explore other stations and components to, see if this pattern still holds. But we can see perhaps, one cluster, some spatial organization within the different earthquakes. And so this might be able to spur some scientific questions. Is the source mechanism for these different than these? I think I have, yeah. So looking at the silhouette, the data points with the highest silhouette scores from those 3 clusters, we can see them plotted here, cluster 1, cluster 2, cluster 3. Now you can see why I took out cluster 2. These, these very well may be picks, but they don't really look like it on this station for this component. And they also were kind of spread out everywhere, not really defining a fault structure. So just for ease of visualization, I took them out. And we can see that certainly these earthquakes have different characteristics, varying frequency content, varying duration, different signal to noise ratio. I should mention here that our data all need to be the same length, so they're all 20 seconds long. Or whatever they are. And then just to make sure we're not just sorting things by magnitude, which happens more frequently than I like to admit. But we can look at a box and whisker plot for the different magnitudes by cluster. And so we can see cluster 2 has smaller magnitudes, noisier, makes sense. And then clusters 1 and 3 actually have fairly similar magnitudes. So it's not necessarily that this just has a lower signal to noise ratio and maybe the same structures in this. They do seem to be, well, I guess it could still be that, but it's not just magnitude dependent. And I think an interesting application for this, for those of you who are building enhanced machine learning or machine learning enhanced catalogs, is this might be a good way to see if you have bad picks. I think it would be definitely worth it. Some of these machine learning catalogs, it's, as was mentioned earlier, they're not known for accuracy and precision. They're known for bulk. And so being able to kind of trim down that bulk, get rid of maybe some of the less confident picks might be, it could be a good utilization of this. And so just a quick summary. We've identified different families of waveforms. We didn't use templates. We didn't use cross correlation. We just inferred the structure that was inherent within the data. We found a spatial relationship, distinct waveforms, and they're not magnitude dependent. Could this point to different kind of fault mechanisms or fault conditions? And a good next step would be to compare other stations. Okay, so I'll stop right there for now and take any questions you may have. Everything was perfectly, okay, yeah.
And I want to add one more thing, but 200 more density. Can I do this application or I have to redo everything?
So the good thing is, say you've got, 1,000 earthquakes and you want to just add another 100 to. So you've already trained your model, and assuming that those earthquakes don't have really different spectral characteristics, you'll still be able to decompose them into the activation coefficient matrix and then into blah, 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 into fingerprints. However, you would want to recluster your whole data from the start. Yeah.
I have a question about like some of the parameters, for example, the window length that you use for the spectrum.
Right.
How consistent is your final result with your cluster if you pick like a different number?
Um,
How sensitive is your robot with your result?
It really depends on what you're going for and what your data are like. So I've done experiments with tremor, for example, and in that case, it's very insensitive to parameter changes. When we were doing the repeating earthquake work, because we really want each and every wiggle to line up, we picked a much smaller window size for that. So it takes and those choices can definitely, in that case, will really affect your results. And so parameter testing is an important part of this process. Yeah.
You said the correlation. I was curious how much of a computational problem is this compared with if you actually just do the correlation? No idea what the computation is.
Right. Yeah. So it depends on your algorithm. Like I know David Schaff has really, really fast algorithms, but they may not be available like as easily accessible to the public. I think for your run of the mill cross correlation algorithms, of course, they're increasing, time complexity of n squared. And it's a similar time complexity for the SpecUFX algorithm. So you may not be saving much time, but it is a complementary method. And, if you're calculating locations, which you probably are, you're probably calculating your cross correlation tables anyway, for double difference location or what have you. So this is just to kind of, it's a different approach, not to replace it.
Second text to the law, this is. Then correlate every pair of them. Just, I think very efficient.
Right. Yeah, yeah, so, yeah. So. Any other questions? Yeah. Say that again? Yeah, so the question is, can we use this to discriminate between induced seismicity and natural earthquakes, right? I don't know, that'd be a really interesting experiment. Yeah, I'm not sure. I'm not sure. I'd be happy to see an attempt of that, yeah. 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 You could do just the coda. Yeah, you don't need the full signal. In fact, this algorithm was adapted from speech recognition and audio information retrieval. So it doesn't really know, that it's an earthquake or not. It's just looking at waveform. So any waveform will do. Any other questions? Okay. So I was gonna take a break here, but I'm thinking maybe it might be good to start the process of doing getting on the cloud, and then we can break and troubleshoot if needed. So let's take 10 minutes. Oh, yeah. Well, we'll be a little bit off, but that's okay. Well, yeah, that's fine. Whatever. Who cares? Okay. So just like this morning, go ahead and log into your AWS console using the username and password that you were given this morning. You may be asking, can I use the same instance this morning? That is a no. You remember you used the ARM architecture, but we're going to just be using the default architecture for this one. You don't have to make sure you're in the West Coast region. That's optional. We're not going to be pulling data from any of the S3 databases, so it doesn't really matter. We're going to navigate to our dashboard and then click the launch instance button. This is where we choose all of the different settings for our instance. So you can choose any name. Instance type, you're going to do T2 large. Remember, this is so that we have more processing power. Just like before, networks settings, you're going to select an existing security group and choose default. And then change this to, so I didn't mention this, change this to 20 or 30 gigs, whatever. T2 large. Yeah. So again, just pick a name of your choosing, the instance type, large or medium, larger, anyways, fine. Network settings, select existing security group and go to default. I forgot to mention this, you're going to want to bump this up to 20 or 30, and then you can launch the instance. Let me, yeah, I'll just keep going through the slides and then I'll leave the slides and do it in person. Yeah. So leave it standard. I think it's underscore x86 or something. Any other questions? Raise your hand if you need help, and maybe someone will help you, but maybe not. You can just raise your hand for good luck. You're not creating a key pair, so don't worry about that. Okay. Okay. Everybody who's still stuck on these steps here, raise your hand. Okay. All right, so no sweat. We've changed our security system or settings. We've added a bit of storage. We've made sure the instance type was large enough. When we click the launch instance, this window will pop up. We're going to proceed without a key pair and then launch the instance. Any questions about this step or the previous steps? Raise your hand if you need help, and one of us will come help you. Yeah, just a reminder, please don't use your earlier instance from this morning. And if you get stuck, you can always cut it and try again. Yeah. No, don't do ARM architecture this time. Do not do ARM. We are armless. Okay, so now you've clicked launch. You've selected proceed without key pair. We don't have a key pair. Okay, people are looking up here. I think that means we're ready. So we're gonna, hopefully this green box has appeared. We're gonna click this link. It's gonna bring us to another link down here. You'll see the name that you gave your instance, and then the instance ID is a blue link. So you click on that. So again, once you click launch from the previous screen, you should be brought to this page here with a green bar, and you can just click on this link. Then it'll bring you here, and you click on this link. And then you'll see this pop up on the side of your screen. And you're going to want to eventually click connect. For me, it takes a minute usually. You might need to refresh the screen. So I'm gonna take it. Yeah. Okay, so once you click connect, does anybody raise your hand if you're on the clicking connect step? Okay, cool. Right on. I like that. Okay. So when you click connect, this window will pop up here. You don't want to click anything, just leave it where it lands and press connect again. And if all goes according to plan, you should open a Linux terminal, which has a beautiful bird of successful cloud connection, but it is otherwise a blank machine. So I'm gonna stop sharing this screen real quick. I'm gonna go over to the terminal. To the console and see if I can actually do this. All right. So, AWS. Okay. So I'm gonna launch an instance. Oh, I guess I'll go to dashboard. Dashboard. We can launch an instance. I'll call it SAUI test 4. You don't touch anything. It's 64-bit. x86. We'll change the instance type to large. We don't need a key pair. I'm gonna go quickly now because I think everybody's done this. Default. Change this to 20. And that's it. Launch instance. Proceed without key pair. Maybe I did that. So yeah, that's this button right here. Launch instance. It's thinking, okay, we've got the green bar. We'll click on that. Click on this. Wait for the connect to enable. Refresh a couple times. Okay. Connect. We don't change anything here, but we're going to connect there. And so if you want to follow, or if you want to view the slides, I put them in the Slack channel here. And if you want to see just an HTML of the notebook, that's this here. So it's just a static notebook. Do you have a question or do you need some help? Hey, Kai Wen, can you help somebody with it? Okay, so oh shit, I'm so sorry. I did stop sharing the screen. Thank you. Okay, we're all gonna see each other. Okay, I should, it's good? Okay. Sorry, Zoom. A lot to handle here. Okay, so we're here. I'm gonna refer you all to the Slack channel. We're gonna go to the notebook. Like I said, it's just an HTML showing the Jupyter notebook that we're about to run, but we need it to run it, so that's why this is here. So everybody go to that link, or it's sowilabs.com/cloud.html. It's also in the HPS book. I just didn't update the link yet. So we want to go here because we're just going to be copying and pasting a bunch of commands into the terminal. Like we've learned before, the when we open a new terminal on the cloud, it's a completely blank machine. So we need to build it up from the ground up. And so these lines are, we're getting Docker, we're downloading Anaconda, and that's about it, initializing them. So I'm at this link here. Again, that's in the Slack channel or just sowilabs.com. You can go there and then it's just this top link here. You can go to the notebook. And yeah, we're going to set up our environment. So just simply copy this and put that in your console. Hit enter and it'll download Docker and set up Anaconda. While that's going, I'll describe the next block. So in this block, we're going to be starting Docker and making sure it's enabled for us as users. Okay, so hopefully that didn't take too long. I'm now copying the second block of code, the sudo service docker start, and the next 3 lines. Anybody getting, oh, what do you got there? Okay, we're gonna take a, are we? Yeah. Well, we'll pull the thing first. Okay, finally, just go ahead and run the pull command. So you've set up the environment, you've set up Docker. Now we're just going to use this Docker pull ghcr.io SciScope specufx label of tutorial and put that in your terminal. That'll take a minute to download, and let's take a 10-minute break. So we'll reconvene at 2:10. You know, get a coffee, or if you need help, this is also time to troubleshoot. So yeah, take a 10-minute break real quick.
But it's not. No, I like it. Yeah. Yeah. Oh, yeah. Oh, yeah. This is where they provide.
Oh, I need the perspective.
You have. Then involved in- There may be some preference. Right. And, you said and you just assume that.
Okay, everybody, let's reconvene. Hope I walked around a little bit. It seemed like most people were able to get onto the cloud. So good job, everybody. And a huge thanks to you for helping doing some debugging and updating. So as some of you probably noticed already, this is going to be a little bit different way of launching our Jupyter notebook. I think I'm good on Zoom. I think I'm good here. Okay, so remember we've got our console. We've just pulled our Docker image, but we haven't launched it yet. We're going to get that command back from this sawilabs.com/cloud HTML thing. So this was the last command that we executed, and now we're going to do this one. So let's take a second and parse what's going on here. Of course, we're running the Docker image. We're using now port 80 instead of 8888. This is I forget why we're doing this, but but we are. I mean, one advantage is that you don't need to choose a specific region. We're pulling this tutorial, no hup. I wish I could. I actually can't parse this at all. I don't know what these mean. We just did this morning, but this is the important thing. Identity provider dot token equals scoped. So normally when you launch your Jupyter notebook, you get a token, then you just enter that token into your password. We've taken that out. So when you launch this command, there's actually not going to be much output. That might be confusing at first, but it's okay. So all you're going to do is you're going to copy this command, go back to your terminal, run it, and say, hey, nothing happened except this little bit of output here. That ampersand signal is just porting the output to somewhere else. And so from here, we're going to go back to our instance console. And we're going to use this address just as it is, actually. Now, don't press open address, because this actually goes to a specific port that we don't want to use. We just want to use the raw address. Just to show that again, this was in the public IPv4. You can get here by clicking on, instances and then finding your instance, clicking on it. And it's this one here. You can click on this double square here. Looks like it's not working for me, actually. That's weird. Well, I don't know. Something might have happened with mine. I saw other people logging on okay. But when you do have the Jupyter hub launching, then you're going to type in scoped. So it'll just be this on the other side of this token. So you'll use that to log in, and then hopefully the notebook will launch. I saw a few people launched it. Is anybody else getting hung up here? Yeah, you are. You had the same. So now I'm having. Connor, are you getting hung up or you're just stretched? What's that? Oh, thank you. Well, that's fun. All right. I'm just gonna try again. For instances. Okay. Terminate your instance. Default. Instance, proceed with instance. Thank you for your patience. I will mention that if you are interested in running this locally, we do have a GitHub that's being developed constantly. And so you can run it locally. I did my whole thesis basically on a laptop. So it's as long as you're using like if you're analyzing less than 5,000 events, you know, less than 20 seconds sampling rate of a normal kind, then it's pretty like compact. So yeah, I'll put the GitHub link at the end, but it's also easy to Google GitHub SpecUfex. Okay, let me try this again. Raise of hands. Is anybody able to get onto the notebook? Oh my God, everybody's ahead of me. Okay. That's great to hear. Oh, it's the wrong one. Well, in case anybody wants to relearn how to do this, I'm just doing it live right now. If anybody's having problems, raise your hand and Kaiwen will try and help you, unless it's the same problem I'm having, in which case, please help me. Yeah, yeah, I just had to redo it. Hopefully that works now. Should have left the old one open. Well, you know, the tutorial guides itself, you'll see there's certain blocks that are green. Underneath these green comment boxes are things you can try to alter. So parameters, for example, not the paths, but your bandpass filter for your spectrogram. You can change the spectrogram parameters, and I'm not going to go into those right now, but you can look at the docs I'm using the SciPy spectrogram method. Time resolution for your fast Fourier transform. So this is done in samples. So we're going to have 64 samples, overlap of 25%, and some padding. All of these parameters are actually quite important. They'll change what your spectrogram looks like and thus your results most likely. We then have some SpecUfex parameters. You don't need to edit these now. So num patterns, this is the initial number of patterns that the NMF step begins with. However, as it iterates through, it'll remove patterns that are no longer contributing to like successful learning. And so that number of patterns will reduce over time. So you just pick an arbitrarily high number and they usually get reduced down to 30 or so patterns. So first, this is part of the reason why we're able to scale up this method is it's based on stochastic variational inference, which is basically taking batch sizes of your super large data set assuming that those subsamples contain the similar distribution as the overall data set, and then you just redo that. And so this is your batch size. You can edit this to be bigger. I probably wouldn't go smaller. Number of states, like I said, we've been using 15, but you can, you know, maybe if you notice that your fingerprints are really sparse, there's a lot of dark spots in them with not information, then you can reduce that. Or likewise, if there's a ton of states that were learned, maybe you want to increase it, see if you can get more complexity. And then the number of examples, you know, how we pulled out some of the waveforms based on the silhouette scores. So this is taking the number of examples, the 10 examples from each cluster with the highest silhouette score. So we're going to look at those. Let me see how this is going. Let me just try this one more time. Is this the right one? Ha, okay. Scoped, log in. Now I'm caught up with you all. Okay, so we're going to be looking at the Amatrice tutorial notebook. You can go ahead and go up to the top panel, kernel, restart and run all cells just to get things going. A couple things take, you know, a couple minutes to parse, so you can just go back up to the top. Because we have a little bit of extra time for this tutorial, I'm actually going to talk a bit about pre-processing the data. As we all know, people who've worked with data, it's one of the most difficult and frustrating processes. In this case, we're just going to be formatting it into an H5 file. And that's the format that is used in a lot of machine learning algorithms and also in this particular tutorial. And so if you're interested in running your own data for SpecUfx, I would recommend locally downloading this, and then you know, you have your waves on your local computer, and you can try to format them. And so basically we're loading some waveforms. The waveforms aren't on this container. I wasn't actually expecting to do this today, and we wanted to keep the container like lightweight, so we didn't include the waveforms. But you basically read a pick folder from that was the output of Kaiwen's phase pick algorithm. So we've got a catalog of picks. We've got, yeah, we're just parsing that. We're selecting a random subset, so we just wanted 1,000 of them, converting their ID to date time objects, makes it nice. We're pulling out waveforms and then making a catalog. We're checking the length. So this is important. Like I said, they need to be the exact same number of samples. So sometimes I noticed from Iris, sometimes they'll do a bit of rounding. So you might have 1,000 samples in one, 1,001 in another. So it's just checking. We can plot the waveforms. This is all of the stations, all of the waveform, or all of the events in map view. And then the blue ones are the ones that, the 1,000 that we pulled out for this. And finally, we create an H5 catalog. It's at the very end here. And so basically what we're doing is we're opening up what's called a store. H5 files are, it's hierarchical HDF5, so hierarchical data format. Basically looks like a file directory like you would see on Finder or whatever the Windows equivalent is. And so you'll have what are called groups, and those are basically folders. And groups can hold other groups, or they can hold data sets. Data sets are basically NumPy arrays. You can format them to put strings in there. You just convert it to bytes or something. So yeah, so a couple funny things about HDF5 files. We call them stores, and you don't want to leave the store open. You have to close the store. And so this is what this line is, with this H5 file being written as F. And then we have this F variable that we're altering. But once this block of code is done, the with statement is finished and the store gets closed. So when you're working with H5 files, this is the kind of format that you're going to use, or else you might try and open up your H5 file in another code and you won't be able to, because it'll pull an arrow. It'll say the store is already open. It's very irritating. H5, a bit of a learning curve, but totally worth it. Okay, that was just a slight detour. So what we're going to be doing in this tutorial for the next 30 minutes is reading the waveforms from an HDF5 file, 20-second records from short period seismograph filtered between 1 and 40 hertz, windowed 3 seconds before and 17 seconds after the P wave picks on the vertical station. And we got those picks from the PhaseNet exercise that we did earlier. We're going to convert the waveforms into spectrograms, filtered and median normalized. That's just to kind of help the machine learning algorithm. We're going to run SpecUfects on those spectrograms. We're going to do k-means clustering evaluated with silhouette scores, and then view some of the trends of the data. And we've got some publications and references here. Okay, so we've run the notebook already. Everything should be done, but I'll just point out things and run cells as I go. We've defined a couple helper functions at the beginning. This is actually the input is a data frame of your features and the number of clusters that you want to check. And so basically we're checking from 2 to 10 clusters here. For each cluster, we'll calculate k-means and then calculate the average silhouette score. And we'll go from 2 to 10 clusters and do that. And we're going to output the clustering number with the best silhouette score. So that's what this one does. And then this is just a helper function to get a spectrogram from the H5 file. We can see there's this with statement again. So like I said, we're setting our parameters here. This block here, we've downloaded the prepackaged HDF5 file for this tutorial. And just moved it around a bit. So hopefully that loaded okay for you. What are we doing here? We're loading the HDF5. And so basically we're just assigning all these variables based on the catalog in the H5 file. And then we're putting it in its own data frame. Maybe a better way to do this, but this is where we're decoding the date time and making it into a datetime object. So here we are creating the spectrograms. We've already defined all these parameters in that block that we saw earlier. This is non-negative matrix factorization, remember, so we need our spectrograms to all be positive. We want to make sure there's no nans showing up, that there's no negative showing up. We filter it just kind of like a boxcar filter. It's not tapered or anything. Yeah, just some normalization and quality check. And here we have our original spectrogram and then our normalized spectrogram. And so we can see that already we're kind of improving the image quality here. So now we're going to run SpecUfects. That's done during this code here. We're instantiating the NMF model. We're inputting the number of patterns and also this catalog of short time Fourier transform spectrograms. And yeah, so here we're initializing it with its shape. Here we're actually running it. I'll run it again because it doesn't take very long. We can see there's a little timer. We only had a batch size of 1,000. Normally, if I'm doing this for research, I might pick something like 10,000 or more. So this is just purely for time constraints right now. Once that runs, we're able to plot the dictionary. So this is frequency as a function of pattern or pattern number. And yeah, we can see our nice dictionary showing up. Okay, then we're going to be doing our HMM step. I already described these before. Sorry. Oh, yeah. Sure. So when we're learning a dictionary of spectral patterns, basically what we want to do is find which spectral content within the spectrograms are most important. And so, maybe the lowest frequencies or the highest frequencies, they're not as important. And so we can see like, especially higher frequencies, you probably don't have a lot of high frequency noise. And so you can see that these patterns here that are more around, centered around 50 hertz, 60 hertz, they're less intense than the ones centered around, 5 hertz here, because that's where more of the frequency content of the earthquake is going to be. However, of course, there's, a full spectrum of frequency content. And so we do want to capture that as well. We notice that these are they're actually gamma distributions, but they look like normal distributions. And so there's some overlap. And so you can actually express what the frequencies are of the spectrogram without using all of these bins. You can see each pixel is a bin, and that's much too fine grained. That's much more fine grained than we need. We don't need bins for every single 0.01 frequency or hertz. Instead, we can say like, oh, we're going to model it as a Gaussian or as a, whatever, gamma distribution over a frequency band. And in that way, you can kind of like get similar information, but you're using now just, a mean and a standard deviation sort of thing rather than each single pixel. Does that make sense? Okay. Sure. Yeah. So, yeah, right. So yeah, I have discussions with my collaborator about this too, but he argues as long as you have enough batches NMF. So yeah, we have batches NMF, that's going to be like 1,000, and then batch size is 1, right? Yeah. So I think I said that wrong. The batches NMF, that's going to be 100,000 or 10,000, like just a big number, so that you're iterating. It might be overkill, but yeah, that's basically how many times you're teaching on a subset of the data. Yeah. Any other questions up until the NMF step? Yeah. Yeah, so oh, the Markov chain. Where is the Markov chain defined? So we haven't gotten to the hidden Markov model yet. That's going to be down here, and this is the chain here. So it's different. This. Sorry, I'll go up a little. Yeah, the Bayesian non-parametric NMF, that's just the flavor of NMF that we're using for spec effects. So it's, yeah, Bayesian process, it's non-parameterized. We're learning the parameters for the gamma distribution for the frequency patterns. Oh, how is it defined? So yeah, a mathematical description is given in the original publication. I don't think it'd be super useful for me to like show it right now, but I'll put in the Slack a link to the paper if you want like a more thorough statistical description of these algorithms. Yeah. Okay. So let's see here. We've got, we can now compare our original spectrogram or an example of one of the spectrograms and its corresponding activation coefficient matrix. And, this is a point where if I were doing this research, I would now loop through this process really try and play with the different spectrogram parameters and see what the activation coefficient matrix looks like on the other side. You know, basically, you know, depending on what you're looking for in your data set. Okay, so like I said, we throw away the spectrograms and the dictionary. All we have is the activation coefficient matrix. Okay, so now we're using the hidden Markov model. Yeah, there's some parameters that I typically don't touch, but you could certainly play around with them. Yeah. This shouldn't take too long to run. But what we get out of it is our emissions matrix, which is showing for a given state. Sorry, this was flipped on the side in the other picture, but for a given state, what kind of frequency patterns is it most likely to emit? Okay, this block here is where we then count the transitions between the state sequence matrices. So again, we're maybe going here, we might see a bright element on state 15. We could expect to see that. So we've calculated the fingerprints. That should be fine. And then we can see an example of a fingerprint. And yeah, state, well, it's labeled 14, but you know, it's the last state. So there's a bright element there. Okay, so yeah, from this step, you can reiterate, play with parameters. But we are going to save all of that output to an H5. So again, here's our with statement. If we're going to basically like delete these these groups if they already exist, because we just want to start a new one. And then for every ID in the catalog, we're going to create a data set that's named after that ID, and that contains the fingerprint. So in our HDF5, we're basically going to have a folder with a bunch of links, if you will, that are named by the event ID of the earthquake, and then you'll get a fingerprint for that station and component. And yeah, we just have a bunch of parameters and output. We're just saving it all in the H5 file. It's really useful for that. You can really build a structure that has metadata, has the actual data. So here's another place, a green block where you can alter the clusters or alter the code. So right now we're searching between 3 and 20 clusters. Sometimes it might have a local minimum, like it really wants to just split into 2 because it's, you know, a blob and it just wants to be cut in half. But maybe you want to explore, you know, what happens if you force it to have more clusters. So in that case, you might bump this up to 10 or something and see, so that you get, you know, a minimum of 10 clusters, but we'll do 3 for now. I am just randomly, or I'm setting the random seed generator at the top so that, but you don't have to do that. You can run it as many times as you want, and it'll, for the k-means part, it'll initiate different centroids for each random state. And so you'll get slightly different results each time, most likely. So here we are, we're calculating k-means on 3, 4, 5, etc. clusters. In each of these iterations, it's also calculating the silhouette score for all of the points and storing it. And then at the end, it'll see who has the highest average silhouette score. And it'll say, okay, 4 clusters was best. And, you know, like you can also say, if you know you want 9, you can just go from 8 to 10 or 9 to 10. I think that works. Yeah. And then, you know, you'll have 9 clusters, but I'm just going to bring it back to 4, 8, 4. Okay. So now we're back to 4 clusters. Okay. We'll plot the silhouette scores. We saw this plot earlier. It's just the number of clusters. Well, we only had 1 cluster. That's at 4. Let me put this back to that. But normally we'd see a plot here with a star where the highest silhouette score was. With 4 clusters, I've created a color map here. You can have up to 12, I think, clusters. but basically your K opt is your optimum. K for K means clustering. And so this number will change and you'll just get a list of colors to assign each cluster. And from this, we can kind of look at the spatial, the spatial patterns that, or lack thereof, that appear. So yeah, right now it looks very cloudy, not very good, but I kind of see like in this depth section here, we have a orange one and a red one that are kind of showing up, whereas the blue is a little bit more scattered. I'm not sure what's going on with green, but let's see your orange and red, that's 2 and 4. I want to keep 2 and 4. I'm going to remove 1 and 3. And so this is where we get to play around with with visualization and clustering. So if you want to remove a couple clusters, you can just copy this here. What did I say? I want to get rid of 1 and 3, right? Yeah. So I'm going to say remove these clusters, remove 1, remove 3. I think I did this wrong. Okay. Let's see, 2. So now we should be removing, I'm just saying like the catalog, where the catalog is not equal to cluster 1 and the catalog cluster is not equal to cluster 3. We're going to make a new catalog and then plot it. Apologize, the colors aren't going to match as well, but we can start to see there's some spatial separation between clusters 2 and, or whatever these ended up being, 2 and 4. So yeah, as I showed in the slideshows earlier, we could see a little bit of spatial separation. This is something you want to explore with a bigger data set with different stations, but it's at least, an indication. So we can now look at the top examples of each cluster, get an idea of what kind of events are existing within these clusters. We can see the spectrograms that went into SpecUFX. These are for each row is one of the 4 clusters, and each column is one of the top 10 examples. So example 1 has the highest silhouette score in cluster 1 or 2 respectively. Any questions about that? Does that make sense? Okay. Yeah. So, yeah, I mean, it's unknown right now. It could be another event popping in. I think we'll see, in a second, because we'll look at the waveforms, which are a little more clear. There's actually, I believe, some like secondary arrivals in the other waveforms. Yeah, like so this is the one we were looking at here. Sorry, let me zoom this in a little. Oh, that's not working. But we can see, there's like a little bit, maybe it's it's just speculation right now, but it could be, this one could be another earthquake, but we can kind of see why these are clustered together. Like they're longer duration, kind of lower frequency. They've got this structure in the coda that may be, a reflection or maybe another earthquake. Certainly some other earthquakes or something happening here. You can compare that to cluster 4, where you can see there's quite a bit of noise in the coda, possibly from instrument noise. We'll look at that magnitude and see if it's simply a lower magnitude that is like not reaching above the signal to noise ratio. And then of course these ones are very distinct in that they're like shorter duration, higher frequency. So yeah, and like I said before, we want to just check the magnitudes. So we can see magnitude 3 is the largest. That's not super surprising. They kind of look like larger earthquakes. It's not too different from cluster 2, however, like maybe is slightly higher, but the medians, you'd want to analyze that to see if there's any actual differences between those distributions. Meanwhile, these two are fairly similar as well. Interesting because cluster 1 does look like mostly noise. So this might be one that you double check in your catalog to make sure the associations are right. So these all went through Gamma, were associated, were picked through PhaseNet. But you might go through, check the probabilities, check the associations, check other stations, see if it's just this station that these are noisy. But we also get a bit of sorry, it's the wrong color there. It's the blue ones here. So you can see they're kind of spread out a little bit more than the other ones. They're not quite as like, so maybe they're just farther away actually, or maybe they're bad picks. Oh, and then you can, so we've got a catalog now that we can look at. So I didn't show this, but this is our catalog. Where we've got the event ID. Oh yeah, these aren't actually from any, this is just the PhaseNet machine learning enhanced event ID. So I've just made up an ID, but we got a location from HypoDD, and we got a magnitude, origin time, waveform. So this is, and the cluster assignment, of course, and the silhouette score. So, you can play around seeing if there's any trends in these data. I was looking to see if there was any depth trends, and, maybe not. Yeah, so that's all I have for the tutorial for today. I encourage you to maybe try playing with spectrogram parameters, clustering parameters, viewing different clusters, viewing, sky's the limit. It's a lot of fun. Another cool thing is once you've got your fingerprints, you can try different clustering algorithms. It's like fairly easy to swap them out with another if you're using sklearn because they have a common format. So yeah, and if you're interested in using SpecEffects for your own data and you want help with that, it's kind of my, thesis baby. So I'm more than happy to spend time to help get that up and running. And other than that, that's all I have for today. So I'm happy to take any questions the last 10 minutes. Okay, well, we've got 10 minutes until the next session. I encourage you to, stretch your legs or play more around, get a coffee, and we'll meet back at 3 o'clock. So the last 10 minutes, you guys work on that.
Yeah, sorry.
Oops.
It's like,
Yeah, I stuck it in here so it's not wiggling around as much.
Oh, sorry about that, people online. Okay. So anyway, the way we're going to do this is I'm going to give this presentation, but on the side, you need to have this. We're going to have a notebook. Whoops, I went the wrong way. Running, that's this. You should have gotten instructions that Ian sent out on Slack. There are like 3 things you need to run this notebook. You can run it locally. You need the notebook file. You need to have downloaded the MISPAS Docker container, and you need a data file. That data file needs to be in a directory called WF in the same folder you have the notebook. So if you do that, we can run this. If you don't, then just listen and set up the thing later, and you can just run this little notebook. So I'm going to actually start this notebook and just show you that, it should just run. I'm going to just go here and start this thing, and it'll run while I'm talking. Let's see, where am I? I got to remember which way I'm going here. There we go. Okay, so you can play with that a little bit, and then I'm going to blab at you a little bit. I think I can put this guy full screen now. So that's what the silly acronym stands for, Massively Parallel Analysis System. What's important about that is this was born out of an idea that, Ian Long and I are the developers of this, of the frustration of how archaic our entire software infrastructure was for doing basic low-level data processing. A lot of that was related to the fact of a lack of a consistent way to handle parallel processing, which I think MISPAS has solved. The second part of it is that it's for an analysis system for us, not something some computer scientist developed. And so it has things in it that, from experience of us anyway, about making it a little more like what you need to do. So I think it's important first to have a short discussion here about, I think it's important to realize that MISPAS is a piece of code to support seismic research. What do you think I mean by that? Anybody? What is the distinction about what a piece of software is to support research? Exactly. And the contrast is this, that most of the so-called enterprise software and a lot of classes of things that you use are things that are made to solve a specific problem, and they do it very well. So, for example, Microsoft Word, or something as big like Antelope, or some other real-time system. They solve that problem, but in research, a research system has to be flexible enough to solve a lot of different kinds of problems. In a production system, that time is money and mission critical or whatever, it's got to work. The way I put it is, research performance is secondary as long as the solution is feasible for what you need to do for your science is good enough. And there's so many one-up solutions that all this stuff that's optimized may not be what you really want. But that doesn't mean it isn't important, right? But it's just that should be secondary. Anyway, the other one is there's a bit about a lot of operational systems are made to be easy to run. Whereas things for you guys should all be lifelong learners, and I can throw something that you've gotten all week that you could survive with, that would make most people go, ah. Anyway, so finding the data model could be very, what's that word? So some key things we wanted to do was way to manage large data sets, and for low level stuff, the real grunt stuff, That's what, this pass is not sexy because it does the grunt work. It's not like some fancy, it's like publishable paper in the end, but it's inside, it can be inside there. It's got these things. So anyway, what I'm talking about today is mostly this, because I only have an hour, okay? How it can use to manage large data and low-level data assembly. So, what is it? Well, the few key things are it's a generic waveform processing toolkit. A really important bit about it is scalability. That the same software, you can prototype something on your laptop, and you can then get it, once you get it working, you can scale it up to 1,000 CPUs if you want to. And it's, our paper demonstrates that it does that. So it's probably it's, as far as we can tell, very well suited to run on the cloud from everything we've done. Although we're not going to do that today. It's important that it's likely to become the best tool for doing the low-level grunge stuff when Iris releases their cloud system. Because if you get close to the data and do the kind of low-level grunge stuff in parallel here, you could do a lot more things at AWS or wherever to reduce how much data you have to transmit. So I'm not going to go read all this bit, but you can read this at your leisure. These are some of the things that are in this. Probably an important thing for all you here right now is that it runs in it's a Python thing. That's why we're running in a Jupyter notebook. And that's the Jupyter notebooks can be used as we talk about reproducibility. That's like we've seen all week. The notebooks are a really important key to do that, to put it in your paper to do that. But we also have another mechanism in this as well to actually track a history tracking mechanism, but I'm not going to talk about that all today. There's all these algorithms and a bunch of other stuff here. So now it's a little short sermon here that this is I think you guys really need to recognize what this is and start to use it more. Because it really is a game changer for a lot of the low-level stuff. Like I say, it makes archaic packages like SAC and AH and all those serial processing, if you will, waveform processing toolkits. I wouldn't say it makes OBS-Pi obsolete because we use OBS-Pi inside of this pass, but I would say it supersedes it because it's kind of built on top of it somewhat. It adds functionality that makes it so much more broader applicability than OBS-Pi. In fact, my next slide, I think, is, well, I know OBS-Pi, why should I use MISPass? Well, first of all, you probably don't have to if it's a small number of waveforms. Once you get to a big data set, handling all that data and managing that data as files or a bunch of, anytime you have 10,000 anything, a database helps tremendously. And the fact that there are some other features here too, which is that one of the things that's not so obvious about OBS-Pi, if you've used it for large amounts of data, is what happens when you throw an exception. You have to handle that data and you have to print stuff. What do you do with it, right? That's no big deal if you have a few, but when you have like 10 million ciphergrams and a few of them throw exceptions, you don't want the entire thing to abort because one of them threw an exception. So we have a really well-defined error mechanism, which builds on things from seismic reflection processing to do that. We're going to look at that in this notebook a little bit. The next thing is this parallel processing functionality. It's just automatic. And we'll look a little bit how you do that in this notebook. And it's also because using Docker, you can run it on multiple platforms. It just runs on anything we can think of we've used. So I said that before, reproducibility. Another thing about that I can preach about this, I could maybe brag with like this. It's really exceptionally well documented. for an open source package, because we spent a lot of time on it. I did, especially wrote a lot of this manual. So there are, you could get this thing is on the, this page. Each of these are links to the individual pages, so I'm not going to dwell on it. We're going to look at the user manual here in a minute, but well, I will show you the user manual quick. Let me show you that quick. Make this thing go. Why do I have to escape this thing first? So I'll just do a quick perusal of the user manual. It's, it's a typical Sphinx user manual, but it's got sections. The first part is how to get started. If you haven't seen it yet, you're going to need, there's instructions for launching this thing. But there's sections about, I don't know how much stuff there is here, but use lots of reading about how this works, some of the underground background behind it. It's there. There's lots to read. And I could just tell you, read the manual, and you could probably, hopefully, have a good idea how to run this. But there's also, much like OBSPI, we have a very big, extensive Sphinx doc string, or the doc strings are indexed through that. It's actually from that user manual. There's a link to it. Well, some of the underlying parts of MISPASS for efficiency are written in C++. And there is a bunch of links to the basic underlying C code, but it's kind of largely hidden from you through Python wrappers. You don't really know the difference per se, but it's there. And there's a big tutorial repository, which you should have pulled for this exercise. There's a new directory in the tutorials repository, which is what you're going to be looking at today. So where am I? Keep going here. So one of the things it's not, though, it's not a solution for every problem, right? It's a bunch of, here's 4 problems I would list as are solved problems in our field that we intentionally avoided. So this is not something we need to deal with unless if we support what you can do with it. But real-time data handling. A lot of packages have made the mistake. They think they need to handle real-time data. This is not, this is an offline analysis system. So there are multiple ways to handle event catalogs. We just saw some, okay? That's kind of a multiply solved problem. There are huge packages for handling seismic reflection data that can do a lot better job than MISPASS can do. If that's that, and then there's the archival stuff that IRIS EarthScope has. So I say it's not a universal thing, but it's a good way to get a custom solution for a research problem. So, yes. Well, I don't know. I wouldn't put it that way, but we're teaching in July, we're teaching a class through EarthScope on MISPASS, and we've been working with the DMS people to try to how we can make this go. I think we're ahead of them, actually. I think in terms of how they're actually doing stuff on the cloud system. But that's what we want to do, is make it so it's easy to run this on the cloud. That's kind of our objective as a component off their system, but we'll see how that goes. That's what we're trying to do anyway. Yes. So here's what we're going to play with right now. We're going to talk the rest of the time. I'm going to go through this notebook. We're going to index some mini seed files that you should have downloaded. We're going to talk about how we manage source and receiver data. And we're going to look a little bit about how we read data. And one of the things we're kind of proud of is how easy it is to read data once you've run it through the system. We abstract the process of doing that. I think I have another slide though. And a key to this thing is data management. This was titled a bit about data management, but I think it really is true that a lot of it has to do with a brilliant decision Ian made to push this idea of using MongoDB for this. Because I have become a complete fan of MongoDB for research data. because it is the integrated data within database within this path. There's some words there, but and you can read the stuff in our data management section here. But in a nutshell, good for data management as opposed to a relational database system like MySQL or any such thing, Antelope or any such thing, is that it's so agnostic about what you throw into it. You can throw just about anything into a MongoDB document and it'll take it. And you can, if you nothing else, you can always grunge it up to make it work. And you can, if you index things, you can make it pretty fast to pull out what you want or group things and sort things in whatever you want. So it's there's a bunch of material in our user manual about MongoDB, and there's a tutorial I've written for this that I think you might find helpful. It's more seismology oriented than the kind of things you'd find. There's a lot of online material about MongoDB, but it's kind of all over the place. But anyway, so here's our to the notebook. So let me go to here. So you'll want, this is, you could go to let me go to the user manual first. If you go to this page of the user manual, I'll launch this thing if you haven't, I guess if you haven't followed me, I should have done this to start with, sorry. You go to run this path with Docker, and it has one of these, you CD to the directory you need to go, the rest of it you'll know. And this, you could cut and paste this line. But the only thing that I would advise you to do differently, well, I went the wrong way again, is use this. I think Ian had you download version 2.0.1. That's our latest release. It's the most stable version you can run. So you had to add this :v 2.0.1 to make it be more carefree. It'll run more reliably, but otherwise it's pretty much use that cut and paste line. So is anybody used about that, or you've been running Docker all week? So I think that's this is pretty straightforward compared to that. Oops, that's out of place. That's what I'm doing next. Whoops. All right, so now I got to go back to this notebook. Where did I put it? There it is. So this thing on this little laptop runs for quite a while. It takes like 15 minutes. It's still running here. So I'm going to look at the version. I'll get this thing out of the way here. I have a static version of it that's just running. Okay, talk about it. So here's the first thing this notebook does is fetch some source data. This is an event-based data we're going to work on here. It's going to select. This is just using OBSPy. So it's going to take. It's actually asking for scope TA data from 2011. All the big events over magnitude 7. So it's all the big ones from 2011, of which there were 20. So that takes almost no time at all. So one of the lessons we've learned about current state of where we are in our community, source and receiver metadata are easily done on the fly. There's absolutely no reason not to use web services to manage to pull in the data you need for source and receiver metadata. It's nothing, and it happens very quickly. So you can and should build, what we're doing here is we're going to build a database of source data that's going to be this project. But any given instance, you could load, if you're working on source data, which is this is a pattern for, you could work on continuous data too. But this is a pattern for source event-driven data. So you would take these sources, you would store them, and that's what this does, is it downloads them. And then this part puts them into MongoDB. So this incantation right there is some variant of that incantation right there about database is the way we create our handle for MongoDB. And there's some magic in there, but what you do, that for that little block of, I've copied that little block from notebooks so many times, because every time I start a new thing, I need to do it. The only thing you change is the get, what's that? I'll try, let's see. That better? All right, so anyway, the only thing you change typically is the name of the database. And they're actually, typically the way you do is you'd have every project, you'd probably want a different database name. That's typically how you do it. And then we have, when OBSPI downloads, when you download earthquake information through web services, OBSPI puts that in a Python class they call a catalog. The catalog is fine for that method. People store the files as this catalog out. You could do that. That's what they recommend. But it's much to mesh with MongoDB. It's better we run our own little application, save catalog, which actually repackages the same information. And that's what this next part here just shows you kind of what that does. And it also tells you something about what MongoDB stores. Now, MongoDB has this incredibly dumb name, I think. Computer scientists, I don't know where they come up with this name, why they call that a document. It's the most confusing name. MongoDB is called a document database, but it's the stupidest name ever, in my opinion. If anybody's a Python programmer, because a document equals a Python dictionary, period. They are actually the same, but conceptually, in terms of what they contain, that's what it is. And in fact, the API for MongoDB, when you ask for a document, what you get back, it loads it into a Python dictionary. That's probably the better way to think of it. The data model is everything is a key value pair. The key is some unique string that identifies what's in that container on the right-hand side. It's the value. And the value can be a long list of things, from simple data types to quite complex things. The example here is, other dictionaries. We take the event, the entire XML record that came down from web services and serialize it. So it says, if you want to reconstruct OBSPI's original catalog entry for this event, just unserialize that event. So that's an example of how extreme, if it doesn't fit in MongoDB, you can just serialize it. Pickle. We've done that several times. So that's how this notebook does. Now the next step shows you something about where web services is right now, that hopefully will be solved soon. It took me 2 hours to download the file that most of you probably can pull down from AWS in a few seconds. It's a flaw in the current system at the EarthScope Iris. Has been going for years, but that will hopefully be soon solved. So what it means is, there's a related, there is a related work notebook which is in that. Yeah, it's in that same repository you pulled, that you could retrieve this data with web services. How I got it. It took 2 hours. But instead, what I do is give you these files. It's about just under 3 gigabytes. So it's not that much data, about 30,000 waveforms. And this line actually builds an index. So we don't actually store always, we can, but we don't always store in the database the waveforms. What you store is an index to it, is the mini-seed files, is the way we usually originate things. If you're familiar with CSS database schema, it's exactly like what they call WF disk, WF disk, which is the table that tells you the index and what data file this is, what the directory it's in, and that kind of stuff. But that's what this is creating. And I actually did it in parallel. That we'll talk about the parallel constructs later, but it's just an interesting example that I think it says map. We'll come back to that in a minute. I actually wrote this, ran it in parallel. So it ran those 20 files that ran that as a parallel process. I could have done it, I think above there, I commented it out, I guess, but it doesn't matter. So, so that's our data set for this exercise. It says that's a MongoDB incantation. Let me talk about that briefly. If you're familiar with Python, you know about class naming and so on. So DB, the symbol DB is the name of is the database, top level database handle. It's the database you created at the top. It says DB equals get database. Okay. WF mini-seed is a choice made by us for where that index got written. In MongoDB's jargon, WF mini-seed is a collection. A collection, if you're familiar with relational databases, a collection is exactly synonymous with a table or / relation. It has the same kind of level in the hierarchy. Count documents is a quote method of a collection. Okay, so that's what we have here. This is an object-oriented Python implementation of how to handle manipulated database. So it's important to understand that PyMongo is an object-oriented way to handle the database. So usually most constructs have the start at the top database. If you're manipulating the database, you start at the top of the handle, the name for the database, and then there's something separated by dots with other things with it. So, but the next part of this is graphical QC. Who said you look at your data? That's very true. You got to look at your data. However, it's a challenge to look at the data. You cannot look at every waveform when you have 10 million, 100 billion waveforms. But you still got to be able to do that. Okay. At least to spot check things or to look at things that are trouble. So what this little section talks about is there's two ways you could do this. You could do graphics in MISPAS. One is more NumPy-like. So this is actually matplotlib graphics right here, this one. All we do is just plot the vector data. So all we're doing is, if you look at the plot command, let me show you this right here. I wish it says, first of all, I talked about abstracting data, reads. There it is, db.readData. I actually have to do one line above it. Tell MongoDB, find one. I just find the first document in the database. That's just the simplest query you can make. It returns a doc as a Python dictionary. And then I tell our reader, read data, pass it the document. Oh, by the way, it's in a collection called WF mini-seed. That's not the default. And it returns the data.
D, the data is bundled up in this in the symbol called D. And D dot data is the vector of the sample data. And it looks like a NumPy array. D dot data, it isn't, but it looks like a NumPy array. So you could just tell matplotlib, plot that data. Now, I could have given it a time axis. I didn't do it here. I just was lazy. It's just, because I'm making a quick and dirty plot. It's often a way you'd make a quick and dirty plot of a set of data. We also have in this pass, I'm doing something a little more elaborate. In this case, let's look at the first, this case, I want to count. Well, see, we got, for one event, I got 444 verticals because it's EarthScope TA data. So that's a bit too much to look at in one display. So I got to do something a little bit different here. There's two lessons here. One is our own integrated plotter, which handles the data we use native, called seismic plotter. You just create an instance that says plotter equals seismic plotter. And then this weird incantation, the query was issued above. I limited, I say I'm going to only keep, I only want 10, the first 10 waveforms. Or it'll just, I'll get black plot for 400, try plot 44 waveforms. So that's just built way I did this illustration. So what this is returning in MongoDB, if you're familiar with MySQL or any relational database, has the same generic concept in databases. A cursor object is basically an iterator that moves through the result of the return, the query return. So, you know, up above it said if I had just asked for all of them with that query, I'd have gotten 444 documents. But I limited it to 10. So what the cursor is an iterator that'll return those sequentially. If I ask for one at a time, it'll return those. So that's what I use here. I'm reading the data and I load it as what we call an ensemble, on which I load 10 waveforms. So they're already bundled up as a group. And so that's what that cursor equals. And then I read the data with that cursor. So the result is on the left-hand side where it says ensemble is those 10 waveforms bundled up. And then you plot. The default is this weird kind of mixed image wiggle trace plot, but you don't need, that's not important. So that's kind of where we are now. We built a database. We have we go this far. Well, let's just do something simple that doesn't require anything more. So this next part is a really simple processing workflow, a serial processing workflow, which does, well, here's the steps. It says right here, real grunge stuff, detrend to remove each waveform's, I think I just did a constant, a linear fit. Simple bandpass filter, typical teleseismic bandpass filter, 100 seconds to 2 hertz. Trim out the edges to get rid of the edge transients and save the results. So wrote a little special function to do the trimming. That's no big deal, but it's just a loop. This is a typical MISPass data-driven serial loop to handle data once it's indexed in the database. So the cursor does, yeah, this is fine. I'm going to do everything. Just process the whole data set. Find the 2 curly brackets means everything. So that turns a cursor, points to the entire data set. Here it's 26,000. It could have been 1 million, and it would have worked exactly the same. And so then this line says, read them one at a time. So the cursor sequentially points at one is a list of documents. It can be thought of as a list of documents that doesn't fit in disk. So you just go click, click, click through it, this is a serial loop, so it just works its way through all those documents, reads one, builds a waveform, detran, filter, trim edges, save. So the save is the inverse of read. It's equally simple, except the only thing it adds is a data tag, because typically if you're going to save data, you might want to know what stage I've processed it to. So we always recommend using a data tag to tell what edge saved, so you have a unique save that tells you which one you got. So, oops, must pushed the wrong button there. So then, now it's got time to jump over here a little bit. Questions first, before I move on. So the next thing, I want to go to a little bit different topic, which is parallel processing. I sort of showed you how MongoDB works and how to write a serial process. It's pretty simple, right? Am I that good a lecturer that nobody has any questions? Yeah.
So you have two data, average based on this last, your data. How you handle it, the set
You mean if you already have it spot, we need that.
let's say after this.
Well, okay, yeah, there's a lot. I just showed the example I showed you is starting from mini-seed data. The reader, we actually totally steal OBSPI reader. Any file format that OBSPI could read, we could read. You just have to tell it. You just have to tell it what the format is. There's an argument for read data that says format equals. So if it's a different format, or it's on a file, you could read it and load it into the system. If it's, we have which we're probably going to use for the Iris cloud system may well be this URL. You could read from a URL that you could actually build the data set. And that's what we hope we can do, because that's what would really make the result of a workflow like this completely reproducible. If you had a URL that was going to forever stay the same, that you could say at the beginning, load up these URLs, you could load that waveform definition, then anybody could reproduce that. So that's kind of our vision of how this, it's not there yet because Iris doesn't have the way to do that. But did I answer your question? Okay, great, good. Anything else? Yeah. Well, that's a really good point. The question is about compression. Mini-seed data, if you're starting from mini-seed data, that's always one of the real benefits of beginning your workflow with mini-seed data, because mini-seed data is about as good as it gets with raw data. It's about 1 byte per sample, and it's not, it's exact, right? It's a really good point about, there's a counter side of the problem, which is that when you're actually processing data, every system in the entire universe today uses double precision floats to handle that data. So you got to expand that into double precision floats to do that. Internally, that's the way it is handled, is that the vector is stored as double precision floats. When you write it out, you can have the option of writing it as mini-seed. If you really want to save the data back as mini-seed files, you could do that, or you just say, write it raw. So our experience, actually, we have a writer with raw binary data that is screaming fast. It's written in C, so you could take, if you have especially a large bundle of ensembles, you have open one file and you just dump all the bytes into that file, keep track of the offset of each piece, and then you're done. And That's the fastest read-write method we have is binary read-write, but there's definitely a storage cost. So that's a good point. Anything else like that? I should probably move on because I want to talk about the parallel part too. So, okay. Everybody. So back to this. See if I can, well, you know, I can just do this. I don't need this thing, I don't think. Or do I? Well, I'll go back to this. So the other big part of MISPASS is the parallel scheduler idea. I don't know how many of you have heard of this idea of map reduce. It's like the computer science people talk about it all the time. It's a big deal. But it's one of those ridiculous things that it's particularly the way we use it in MISPASS for every workflow I've seen yet ever developed is overkill, and it's confusing actually. But it's a modern paradigm, and the schedulers we use are heavily used way outside of our field. Where we use these two systems that are integrated in that container called Dask and Spark. How many of you ever heard of those two things? Anybody ever hear of these before? Silence. Okay. See, they're the Dask and Spark are parallel scheduling engines that are used to parallelize jobs in a very generic way that doesn't require anything fancy. What we'll see here in a minute is it takes a tiny change to your little serial job to turn it from a serial problem to a loop to a parallel job. And that notebook, in fact, you're probably looking at it, is the same job run in parallel. And the way that, and it's the map reduce model that allows this to happen. So I want to quickly talk about it a little bit in terms of what it does, that a lot of you are probably familiar with, but particularly from the Unix side of things, was that one of the great inventions that made Unix what it was so popular in scientific computing for 30 years, still to the present, 40 years, is the idea of a pipeline. And some packages like Seismic Unix, which is a reflection packaging, reflection processing package, does everything through pipelines. And so, you know, there's a good, you know, there's an example from Seismic Unix: read data, bandpass filter it, normal move out correction, apply a mute, display the results. This would be a Seismic Unix implementation of that particular statement in shell-like lingo. That's one program, data file, another program. The pipeline symbol is used to pass data between processing chains. A map reduce model is essentially that. So that the only thing it does is add multiprocessors. So the idea is something like a parallel thing like that in the Unix model would process, like Seismic Unix would process one cytogram at a time. Pass it, finish it, pass it down the pipeline, finish it, pass it down the pipeline. What you do with map reduce is, this is an even little quote to be cute, you animated. The first process, they just start working on the data through this. The jargon was called what Dask calls a bag, and what Spark calls a RDB. What the hell does that mean? What does that mean? Resilient distributed data. That's right. What they do is it's the container that's used. We use that container is a data set that doesn't fit in memory. It doesn't have to fit in memory, and it manages that data set even though it won't fit in cluster memory. And so what it does is basically work its way through one thing at a time and hand one job to each processor. And the process, the scheduler decides how it's going to run and sequentially or how it does it. You know, we're actually still trying to figure out what the limits of what it can do are. But anyway, here's a different picture of it, just to tell you the other side of it, which is what's called reduce. The definitive example in seismology of reduce, and in fact, there's only two known examples I know of that I've yet found that are common standard data processing things that are reduce models. Stacking is a reduce operator. The other one is if you have a bunch of single seismograms and you want to bundle them up and put them into one of our ensemble containers, that's a reduce operator, because you start out with many and you end up with one. That's what reduce means. But what our experience is that almost all seismic jobs that I've run through yet, I've encountered can be reduced to map operations, a series of map, which essentially is that pipeline job that I just showed you. So I think this is, I talked about that a little bit, that this is just the words of what I said a little earlier. I was a little out of order, but these parallel containers, BAG or RDD, are essentially a way to, you can think of it like an HDF5. In fact, you could put one and you could read them from HDF5 files, actually. It's possible to originate the whole thing from, we don't have that support yet, but you could originate something from a large container. Anyway, it's basically a way to do that. And there are basically, we use RDD and BAG for the way we do seismograms. There are other parallel containers that are in this automatically that come with Dask and Spark. Some of you know, I've seen things with Pandas data frames today. There is a parallel version of Pandas data frames. So if you have a gigantic workflow that's driven by a giant table, you can originate it as a Pandas data frame. And there's a lot of examples you can find on the web. In fact, a lot of the conversations you see on Dask and Spark talk only about data frames. So anyway, the other one is arrays. You could write, you could do Dask or Spark arrays that are gigantic. They sort of automatically partition the arrays for you. So you basically set up, when you build a Dask array, you can do 1,000,000 by 1,000,000, if you can do anything with it, but you can set up the blocking of the array, and it'll set it up and it'll try to handle blocking the way it depends on your algorithm. But anyway, it's an alternative way to do hand blocking of arrays to handle very large arrays. It's not something we do directly in this pass at the moment, but I just want you to be aware of it. So anyway, one of the big deals, though, I think, is that you'll see in this example too, is that this isn't quite our serial workflow, but it illustrates the same idea. The serial workflow is driven by a for loop, driven by docs. To read data, do something to it, right. That every one of these lines here, what you do is the function that's called read data, trend, well, it's a little bit different here. Things like trend, filter, so on. The function name appears in what's called a map operator. Map reduce. Remember I talked about map reduce? Map is the operator which essentially says, apply this filter. It's just like that Unix filter model. It's exactly the same thing as using a Unix filter, but in a parallel pipeline. So it's really easy to understand that way. And so what you do is you use the function and then any arguments you pass to it afterwards in a whole series of function calls. So they're processed sequentially. So the data flows from here to here to here to here. Now, the only thing a little weird right there is something we've added in Ms. Pass. And you notice instead of saying read data and save data at the end, we've got read distributed data and save distributed. I think we have save distributed data. Or no, I guess I don't have that in this example. I have saved data, but read distributed data is a parallel reader. So it will not, the process is originated and will do each of the reads as it can be scheduled to be done in parallel. Otherwise, it can be a bottleneck. And there's a write version which does the whole thing and makes it run as fast as it can. It's kind of a detail. You don't have to do it that way, but that's the way it could be. That's the way we do it anyway. That's the way we recommend doing it. So now we'll go back to, well, I got to do is end this, I think. So for our example, this does the read and write. And one of the things you'll find if you run this, you probably got the same result I did. The two are going to be not any different. In fact, it might take a little longer to run the parallel job. I didn't compare my numbers. But that's typical on a laptop like this, unless you do something fancy, because it's a detail about the way it does the handling. You have to add some. On a laptop, you typically have to add a few things to make it run faster and use all the cores. Especially with Docker, you have to tell it how many cores you got and so on. It's kind of a detail, but that's why it runs slow, because it essentially runs with one worker. So it's really not any different than serial. But that's kind of the way we usually recommend. That's why I usually start, just make it work with a small amount of data. Anyway, but the real key point is, see, that dtrend, filter, and trip, those three functions that were run in the serial job just appear as map calls. They're the first argument in the map operator. And that's all it takes to parallelize the job. You instead of you replace the for loop by read distributed data, and you change the save data line by write distributed data. And it's all done in parallel. Say, if we run this on, as we thought about doing on the cloud, but I'm sort of glad we didn't have to deal with that mess, right? It just runs. But you could scale, it would scale up on an HPC system or the cloud to run to however many processors you throw at it. So where am I? I got pushed the wrong button again. Okay, where are we here? All right, so I got a few minutes left. The rest of this notebook goes over a couple other things here. I think this is best left to your reading. There's lots of words about this in the user manual about the problem. This is in fact the idea of normalization. MongoDB calls a thing called normalization, that if anybody's a relational database guru, what MySQL or whatever would refer to as a database join in MongoDB jargon is called normalization. It's a little bit different though, because it's not hard coded the same way it works, and it's not as good. Normalization, it turns out, is the process of matching one thing with another. And here's what you can read my words that are written here, but one of the things we found is that the way normally recommended to do this is a really bad idea. And that is, normalization means things like taking that source, those 20 source records, and matching them to every waveform. Or what we load here in a minute is a receiver metadata. Well, that's what this line does. We got station metadata by web services, and it's similar to the way we saved catalog. We'll save what OBSPI calls an inventory object into another collection, but we actually keep it in two things, one called channel and the other one called site. Minor, I won't get into the details there. But here's the point. These numbers tell you the point, which is I retrieved 857 receiver records. We had 20 sources originally. So I have these teeny tiny tables of 20, and I actually have I could make this data set any pill size of you'd see, and it'd be 100 times bigger than that. So I might have 1 billion waveforms, and that number would change, the number of receivers. So I have a small number of things here to match against a giant thing over here, the number of waveforms I have. So anyway, to make a long story short, one of the things we added to MISPASS in version 2, which is out now, is basically a memory version of it, that you load the collection into memory and you match it on the fly. That you load these receiver coordinates or whatever on the fly from memory, like a data frame. And it improves performance a lot because you don't have, there's nothing worse in a workflow than asking the database engine for something. Because it's like talking to the moon. There's a word I have in the documentation about this. It's like, it takes like 1 million, it could take like 1 million clock cycles for the database engine to respond to a query. So you really don't want to do database queries within a computation. And so this is the kind of thing that avoids that. So it's an important feature of MISPASS now for efficiency. And so that's a bunch of stuff in here about that, and you can read it in your leisure. I don't want to take too far. And so the last part is just a more elaborate processing workflow. I do it serial, I didn't do the parallel version, just to give you an idea of what else you can do. You can look at our other examples and our other tutorials to get an idea how to do more of this stuff, or the user manual. And I want to close with this thing. Here's a statement about this. This is actually important to realize about anything. It's like a practical thing. Parallelization is great, but my recommendation is, from my experiences, don't do it unless you have to. If your data set is small enough, you can do it in a couple hours. Don't bother. You still want to use MongoDB to manage it because it'll be so much easier to handle. But if it's still feasible without parallelization, why bother? Because you open up a whole new can of worms, trust me. Especially if you have to go to a big HPC system or a cloud or whatever. And lots of things will tell you that on the web too, by the way. Anyway, but the last thing I want to talk about, and I'll close on this, is an idea this idea has a long history in seismic reflection processing that's not in anything else that's out there in our field, which is, for 50 years in all seismic reflection processing systems, there was a capability of marking a datum dead. And what the system did is, if a datum is marked dead, it'll be just ignored and passed on down the pipeline. And that turns out to be really valuable in this model of MapReduce, because what you do is if you find something goes wrong, what'll happen if you don't have that capability? It's why we had to go to our own version of data objects instead of using OBSPI's trace object, because if you just throw an exception, you'll abort the entire job. If you don't handle that exception, you will abort the entire job. So what we do instead is we create what's called an error logger internal on every data. Every datum has an e-log container. And what happens is, if something goes wrong, we log the error onto this e-log, as post a message there, and mark it dead. And then, so anything afterwards totally ignores it. And that way things just keep going. You can process 1 million records and you won't have a problem. And then it has this thing at the end, we have this colorful name of a cemetery, which is the error log records then get dumped automatically when you save the data. by default. They're dumped and thrown in the cemetery and buried. But the burial means that there's a body laying there, and the error message appears. So it says, in this case, it says data range. The reason that killed it was the data range was smaller than the window. So I know exactly what happened. I cut the data a certain way, and some of the data were too close so I had a large window I was cutting out, and it wasn't enough pre-peak wave time. So it just cut it out. It died. It said, I can't handle this because you asked me for something I can't do. So I'll kill this data and I'll log this message. That's most of them are. But it leaves to let you know which one it was. It leaves a record called the tombstone, which is what the header values were on that datum. So this turns out to be station BHE channel A04AD. So, and there's a lot of these. I just read the last part of this, shows you all the dead bodies, at least what the messages were. And that's typically what you do is after you say, oh, some of them got killed. How big is the cemetery? What I've done here? Oh, let's look at what messages are in there. And you get an idea what some of your problems were. So you can then work your way through and, well, do I care? Well, I lose 50 seismograms out of 1 million, I probably don't care. But if I lose half the data set, I probably should care. Anyway, so that's where you track error problems. I am almost perfectly on time. Well, so I can answer more questions. So, yeah.
You talked about I'm curious, like, can we use MS Pass to invert the dark matrix?
So for the people online, the question was about inverting a large matrix. The answer is yes. That's what this thing I talked about, dask array. If you can, or you can just, if your workflow needs something like that, you could build a NumPy. If it fits in memory, just build a NumPy array and you have to invert something. Yeah, but if it's a gigantic matrix, you could use a dask or a Spark array and block it. You gotta tell it how to block it up. And there are most LAPACK routines are implemented in Dask. I don't know about Spark. They probably aren't. They no. And Dask does though. And Dask has most of the standard linear algebra routines in their array API. So you can, it might take forever, but you gotta know what you're doing. You gotta read the manual about how you block up the matrix for the algorithm you're going to use, but it's possible. Yeah. Yeah. Yeah, if you can write it if it's in Python, it's dead simple. You just write a Python function like this one here. That's this little example. In fact, you often need to write these little wrapper functions like this one. Cut P window. So it does a specific task. So reads an ensemble in and emits one. That you tend to write little Python functions that do other things that you could do something higher level like that. And that's kind of the model mindset you have to develop is like, I want something that brings in a seismogram and emits one. If I can put it in that paradigm, it's fine. Or if it emits something else, what it has to do, that's the first rule about a map operator. It could be anything can be read in, but it has to emit the same thing. In other words, it has to emit a common type. Or at least, I shouldn't say that. It is a common type. What comes after has to be able to handle whatever gets spit out. The output of these things is like a giant list, giant Python list. And it could be anything in there, but you got to handle it if it comes out at the end. So the model we use all the time is you should always input a seismogram and emit one. But if you could also do other things like you could drive a processing loop by a list of source IDs. That defines the grouping. Not making sense. And so as long as, I think I got over answered your question. Yeah. Yes. Well, for the time being, we have we're through scope. We have a couple, we have a year or two left for that. I've pledged before that, I'm a retired professor. I'm doing most of this as a volunteer because I think it's so important. It's a problem I preached about for like 15 years ago. And that we've essentially solved this problem of this kind of grungy middleware between the data centers and something useful after it. So I think my other pledge is like, as long as I'm above ground and with it enough to do it, I'll keep trying to maintain it. But what really the long-term future to make it maintainable is you guys have to take control of this too and help us. It's an open source package. So if it's going to succeed, you have to use it and tell us what, apply the fixes. If you find some new whiz-bang gizmo to add to it, contribute. And we can make this a bigger framework. So that's the hope. And that was. Yeah, and send an issue, right? Something's wrong. This broke for me, right? Carl.
Some perspectives, I was thinking in this pie set tool that you had is an example where we spend many years trying to piece together all the little things to try to make our own food more efficient. And then obviously, it doesn't have like the parallel large data capability that you're motivated by. Yet probably this package doesn't have all the whistles and bells that we might be synthesizing. So figuring out how to coalesce, identify the pieces and I don't know.
That's exactly right. That's this is, like I say, I emphasize again, it's the low level grunge stuff that nobody wants to do. You have to decide for yourself it's a framework where you need to decide for yourself, where's my interface between using this thing to get rid of all this grunge stuff, and what do I need to produce to make a data set that I can run my own whiz-bang thing on?
Your thoughts? I'm getting sort of like almost antelope sense that you could create a large scale database. For you, this would replace like an antelope schema.
Absolutely.
Yeah.
And that's in fact. Yep, exactly. Anybody can do it. It's open source. It's not proprietary. It's like part of why I'm so high on MongoDB is a long experience with Antelope. Some of you may know that I had a long experience with Antelope, and major contributor to Antelope's contrib library. But the thing that was most frustrating me about using a relational database schema was if I did anything different that didn't match the existing schema, it was a freaking nightmare to try to add something new that you could actually manage the data with. With MongoDB, it's like you just add a new name value pair. That's it. So I'm already over, so but what's planned for next, Ian? Okay. Okay.
So I was thinking that for the rest of the day, we could do a poster session again, keep mingling. I think we did a lot of debugging and computing today. So I think we can take it easy for the rest of the day and just enjoy discussing with posters. tomorrow morning, 9 AM, we'll do a group photo just outside downstairs. If you have problem coming in with the locked doors, I understand. Please use Slack to tell us if you're locked, and then I'll come and open. But so please come for 9 AM poster in the beautiful, sunny, warm Seattle. And so that'd be great. Tomorrow, you saw we changed a little bit the schedule. So we're going to do ambient seismology tomorrow with large scale computing on the cloud. So we've done Jupyter notebooks so far, but we'll teach you how to scale up your processes using ambient cross correlation. And then in the afternoon, after our lunches and the code has run on AWS, we'll look at the data and talk about it. But we'll also have 2 hours of lecture on event classification for machine learning for the Pacific Northwest, where we're classifying between different event types. And so we'll talk a lot about the process of data curation, model training, and all these steps that you might find interesting. And I think we may conclude the day with a cheese and hummus at 3 PM tomorrow. How's that sound? Yay. Hey, good job. Everybody's running. I saw the wiggles, and it's just been really fun that you're all following.
So I just disconnect this, right?
Yeah, that sounds good.
They're done?
Yep.
Probably the people online. Pretty much. They're bored.
There's
They're all signing off. They're probably getting there, so, okay.
I was just, so you mentioned the fact that you can do a task arrangement. It would be interesting to do, you have all these nicely arranged seismograms. And so if you can do a randomized SVD, you can actually discover, you can do subspace, a randomized SVD of seismogram, you get to see all the
All
cool
those things,
structure.
all those things. One thing we have a prototype for. It needs more work, though, is essentially a standardization of task arrays where you take. Yeah, if you take a random group of data, you have to worry about the resampling problem.
Yes.
And so, and realigning everything. So we have a
Yeah.
prototype for what we call, instead of the ensemble I showed there, it's just a list, it's just a vector of waveforms.
Yeah.
Um,
Yes.
But with the adder is more like the way side reflection data is handled, but it's a big matrix.
Yes.
And that can be made as a task array.
Yes.
But it's not heavily tested. You can look at it. We haven't implemented, but it's called gather, right?
Yeah, we had a gathering.
Yeah. But it's good. I think you can do like SVDs of seismograms, like the new, SVD is the new much. But randomized SVD, you can get iron modes of the seismogram when they're aligned. You can get nice decomposition
That
of
makes
this, and
That makes sense.
Yeah, so,
compression.
like Gary just mentioned, the task array that can handle a large scale and distribute.
Yeah.
Or another one like
Compression.
that. Actually, another one like that. Is, I thought about the Bostock company did this for receiver function calculations. Use a principal component method where they just line up the diagrams.
Yeah.
And you take the largest principal component,
Yes.
remove it, and that's the,
Oh, yeah.
that's an
That's the
estimate of the
image.
direct image, it's an estimate of the direct, of the wavelength.
Yeah.
So you use that for deconvolution instead of station.
Right. Nice.
So that would be really, that would be easier to implement.
We did a ping pong.
Is that- Oh,
Oh, because you're the.
am I the host? Am I just?
We're still-
Oh,